Here's a promise. Over the next 4 hours, the entire GATE data science and AI syllabus, every subject, from the ground up, is going to settle into your head as one connected picture. Not facts you cram and forget by morning. A way of seeing that makes the exam feel familiar. No prerequisites. Just stay with me. One video. Every topic GATE asks. We start from absolute zero on each idea and climb to exactly the depth the exam tests. No further. If you're a beginner, you'll keep up. If you're revising, you'll find the traps you keep falling for. This is the whole map. 8 lands. Probability and statistics. Reasoning under uncertainty. Linear algebra. The maths of data in many dimensions. Calculus and optimization. How things change and how we find the best. Programming and algorithms. Thinking like a machine. Databases, storing and querying truth. Machine learning, the heart of the paper. Artificial intelligence, search, logic and inference. And general aptitude, 15 easy marks people throw away. Whenever you feel lost, we'll come back to this spine. Here's what you're walking into. 3 hours, 65 questions, 100 marks. On a computer, 15 of those marks are general aptitude. The same for every GATE paper, and the other 85 are your core data science and AI. 3 kinds of questions. Multiple choice. Exactly one right answer, and a wrong one costs you minus 1/3 on a 1-mark question, minus 2/3 on a 2-mark. Multiple select. 1 or more right. But here's the catch. No partial credit and no negative marking. And numerical answer type. You just type a number, and there's no penalty at all. Notice the asymmetry. Only ordinary multiple choice punishes a wrong guess. So should you ever guess? Let's do the maths. Predict the answer before I show it. A 1-mark multiple choice. 4 options, blind guess. 1 time in 4 you're right, for +1. 3 times in 4 you're wrong, for -1/3. Add it up. It's exactly 0. A blind guess is break-even. Neither smart nor costly. But the moment you can eliminate even one option, the expected value turns positive. So, never leave a numerical or multiple select blank. And on multiple choice, guess only once you've ruled something out. Not all lands are equal. Machine learning is the single biggest chunk, and probability and statistics is right behind it. Together, these two alone are close to 40% of the paper. They decide your rank. That's why we spend the most time there, and why this video opens with probability the moment orientation ends. Now, how this video actually teaches, because the method is the whole point. Every concept follows the same rhythm. First, the intuition, in plain words, until it clicks. Then the clean formula. Then I solve one real exam-style problem in full. Then I hand you one and pause. And that pause, where you try before I reveal, is where the learning actually happens. So use it. Then I show you the exact trap GATE sets on that topic, and we lock it in before moving on. A few things to make this work for you. Every part is marked in the chapters below, so you can jump and revisit. When I pause and ask you to predict, actually pause. When a derivation goes fast, rewind. That's not a weakness. That's how hard ideas go in. And keep the spine in mind. Every new idea hangs off one of those 8 nodes. Enough setup. We begin where the paper pays out the most, probability and statistics. The art of being precisely uncertain. Let's go. Probability is the maths of not knowing and doing it precisely anyway. Every claim collapses to one number between 0, impossible, and 1, certain. Master how those numbers combine, and a third of this exam opens up. This is the biggest scoring land on our map, alongside machine learning, so we build it carefully from nothing. Start with counting, because probability is often just counting the lucky cases over all the cases. The one rule that runs everything. If a first choice has 3 options and a second has 2, the pair has 3 times 2. 6. Choices multiply. That's the whole engine. 2 flavors, and 1 question decides which. Does order matter? Lining 10 runners up for gold, silver, bronze, order matters. That's a permutation. 10 times 9 times 8, 720. Picking any 3 of them for a team, order doesn't matter. That's a combination. The same count divided by the ways to shuffle 3, giving 120. Permutation arranges. Combination just chooses. Your turn, predict before I reveal. A 4-digit pin. No digit repeated. Pause it. 10 choices for the first digit, 9 left for the second, 8, then 7. Multiply. 5040. If you saw no repeat and reached for the multiplication rule, you've already got it. A tougher one, the kind gate actually asks, from 6 men and 4 women, form a committee of 3 with exactly 2 men. Break it into independent choices. Pick the 2 men, 6 choose 2 is 15 ways, and pick the 1 woman, 4 choose 1 is 4 ways. Since every pair of men can go with every choice of woman, multiply. 15 times 4, 60 committees. Split a complex count into independent stages. Count each, then multiply. A counting gnat in the style gate rewards. Predict before I reveal. 5 different books go on a shelf, but 2 particular books must stay side by side. The trick is to glue those 2 into a single block. So now you're arranging just 4 things. The block plus the other 3 books. 4 distinct units arrange in 4 factorial ways. That's 4 times 3 times 2 times 1. 24. But inside the block, the 2 glued books can themselves swap order. 2 factorial 2 ways. Multiply the 2 independent counts. 24 times 2, 48 arrangements. Whenever items must be adjacent, treat them as one block, arrange, then permute inside the block. Whenever you see the words at least one, flip to the complement. It's almost always easier. Roll 2 dice, the chance of at least 1 6. Don't add the cases. Instead, ask the opposite. The chance of fuck 6 on each die. So 25 over 36 for both. Subtract from 1, 11 over 36, about 31%. The naive 2 over 6 double counts the double 6. At least 1 means 1 minus none. Burn that in. Now the vocabulary. List every possible outcome. That's the sample space. Any bunch of outcomes you care about is an event. For a fair die, the sample space is 1 through 6, and the event, even, is 3 of those. So its probability is 3 over 6, 1/2. Favorable over total, when outcomes are equally likely. 3 axioms hold the whole theory up. Probabilities live between 0 and 1. Something in the sample space is certain. Total probability is 1. And for outcomes that can't co-occur, you add. From these come to shortcuts you'll use constantly. The chance something doesn't happen is 1 minus the chance it does. And for events that basic and overlap, the chance of A or B is P of A plus P of B minus there. Overlap. Subtract the double-counted middle. Here's the confusion gate feeds on every year. Mutually exclusive and independent sound similar and are nearly opposites. Mutually exclusive means they can't both happen, like rolling a 2 and a 5 on one die. Their overlap is 0. Independent is a statement about probabilities, not pictures. Knowing one tells you nothing about the other. So their joint probability is the product of the 2. In fact, 2 events with non-zero probability that are mutually exclusive are the opposite of independent. If one happened, the other definitely didn't. Don't ever blur these. Conditional probability is just updating your world. The moment you learn B happened, B becomes your entire universe. So the chance of a given B is the overlap of A and B, rescaled by how big B is. That little rescaling, dividing by PB, is the heart of nearly every hard probability question in this paper. Often you can't see an event directly, only through cases. Two factories make our bulbs. A makes 60% at 2% defective. B makes 40% at 5% defective. The overall defect rate is each case weighted by how often it occurs. 0.6 times 0.02 plus 0.4 times 0.05. Split by cause, weight, and add. The law of total probability. Let's finish it. 0.6 times 0.02 is 0.212. 0.4 times 0.05 is 0.02. Add them. 3.2% of all bulbs are defective. Hold on to that number, because the real exam question usually flips it around. A bulb judge is OS defective. Which factory did it come from? That flip is Bayes, and it's next. Here's the deepest idea in this whole subject. The number you can measure is almost never the number you want. A test gives you the chance of a positive given shik. But you, holding a positive result, want the chance your given the positive. Bayes' theorem is the machine that flips one into the other. Picture 10,000 people. The disease is rare, 1%, so 100 are actually sick. Our test is excellent, 99% sensitive, so it catches 99 of them. But look at the other 9,900 healthy people. Even a tiny 5% false positive rate flags 495 of them. Now keep only everyone who tested positive. 99 are truly sick, and 495 are false alarms. That picture as is SO the formula. The chance you're sick given a positive equals the likelihood. The test catching the sick times the prior, how common the disease is, divided by the total chance of a positive at all. Posterior on the left, prior, likelihood, and evidence on the right. The prior is the part beginners forget, and the part gate rewards. So put a number on it. 99 true positives over 594 total positives. That's 1 over 6, about 16.7%. Read that again. A 99% accurate test comes back positive, and you're still only 1 in 6 likely to be sick. Not because the test is bad, because the disease is rare. That's a real NAT answer. Now the flip we promised. A bulb is defective. What's the chance it came from factory A? Bayes? The chance it's from A or chord defective. 0.032 over the total defect rate, 0.032. That's 0.375. So even though A makes the majority of bulbs, only 37.5% of the effective VIX ones are A's, because B is the sloppier factory. Notice the two answers, A and B, add to 1. They must, since the bulb came from somewhere. One more, a classic. 2 coins in a bag. One fair, one double-headed. You grab one at random and flip a head. What's the chance you grab the double-headed coin? Prior is 1/2 each. The double-headed always shows heads. Likelihood 1. The fair shows heads half the time. So, a half times 1 over a half times 1 plus a half times a half. That's 0.5 over 0.75. 2/3. The head is evidence that nudges you from 50-50 up to 67%. Evidence updates the prior. It rarely settles it completely. A fresh Bayes problem, a spam filter, not a coin or a disease. 30% of incoming email is spam. The filter flags 90% of real spam, but it also wrongly flags 5% of genuine email. An email just got flagged. What's the chance it's actually spam? Build the evidence from 2 cases. Spam and flagged is 0.3 times 0.9, 0.27. Heyman flagged is 0.7 times 0.05, 0.035. Add them for the total flag rate, 0.3 or 5. Bayes is the spam piece over that total, 0.27 over 0.3 or 5, which is about 0.885, roughly 80.5%. Because spam is common here, a flag is fairly trustworthy. The opposite of the rare disease case, where the same arithmetic gave a tiny answer. The prior swings everything. The trap, then, is the Bayes rate fallacy, trusting the test's accuracy and forgetting how rare the event is. Whenever a problem hands you a very rare condition and a single positive signal, expect the answer to be far lower than your gut says. Gate sets this exact ambush almost every year. A subtlety worth 30 seconds, because it returns in machine learning. Two things can look related yet become independent once you know a hidden cause. Wet roads and raised umbrellas seem to predict each other, but only because both are caused by rain. Tell me it's raining, and they carry no extra information about each other. That's conditional independence, and it's the exact assumption that makes naive Bayes work later. Independence and conditional independence are not the same thing. Lock in what we've built. Probability is favorable over total. When at least one is messy, subtract the complement. Bayes flips a measurable conditional into the one you actually want, never forgetting the prior, and the Bayes rate quietly decides the answer. That's the foundation. Now we put numbers on outcomes. A random variable is just a rule that turns outcomes into numbers. Flip two coins and let x count the heads. X can be 0, 1 or 2. And listing how likely each value is gives the probability mass function. One head is twice as likely as 0 or 2. So the bars read a quarter, a half, a quarter. They must sum to 1, always check that. Stack those probabilities as you move right, and you get the cumulative distribution. The chance x is at most some value. It only ever climbs, from 0 up to 1. For discrete variables, it's a staircase. The jump at each step is exactly that value's mass. Mass tells you exactly. The CDF tells you up to here. The expectation is the long-run average, the balance point of the distribution. Multiply each value by its probability and add. For a fair die, that's 1 through 6 each over 6, landing at 3.5. A value the die can never actually show, yet exactly where it balances. Expectation is a center of mass, not a possible outcome. The mean is one summary of the center, but Gate expects all three. The median is the middle value once you sort the data. Half lies below it. The mode is simply the most frequent value. Take 2, 3, 3, 3, 3, 7, 10. The mean is 28 over 6, about 4.7. Sorted. The middle two are both 3, so the median is 3, and 3 appears most often, so the mode is 3 as well. Notice the mean sits well to the right of the median, dragged up by that lone 10. That gap is the fingerprint of a right skew, and it's exactly why the median, not the mean, is the honest center for skewed data like incomes or house prices. Expectation has a property so useful, it feels like cheating. It's linear. The expected value of 2x plus 3 is just 2 times the expected value of x. Plus 3, 2 times 3.5 plus 3, which is 10. And the deeper gift. The expectation of a sum is the sum of the expectations. As always, boss, even when the variables are tangled together and dependent. That one fact cracks problems that look impossibly messy. Break the quantity into a sum and take expectations piece by piece. Two distributions can share a mean and feel completely different. One tight, one wild. Variance measures that spread, the average squared distance from the mean. The shortcut you'll use under time pressure is the mean of the squares minus the square of the mean. Take its square root and you're back in the original units. That's the standard deviation. Worked on the die. The average of the squares, 1 squared through 6 squared over 6, is 91 over 6. Subtract 3.5 squared, 12.25. You get 35 over 12, about 2.92. Notice we never needed the spread formula term by term. Min of squares minus square of mean did it in 2 lines. The most important discrete family starts from one yes or no trial, a Bernoulli success with probability p. Repeat it n independent times and count the successes. That's the binomial. Its mean is beautifully simple, n times p, and its variance is n times p times 1 minus p. Coin flips, defective items, correct guesses, all binomial. 5 fair flips, Probability of exactly 3 heads. Choose which 3 flips are heads. That's 5 choose 3, 10 ways. Each sequence has probability 1/2 to the 5th, 1 over 32. 10 over 32 is 0.3125. Choose the positions, multiply by the per sequence probability. That's every binomial question. And the summary numbers fall out instantly. 10 trials, success probability 0.3. The expected number of successes is n times p country. The variance is n times p times 1 minus p. 10 times 0.3 times 0.7, which is 2.1. And the standard deviation is its square root, about 1.45. No summation over 11 outcomes needed. The formulas hand you the center and the spread directly. A binomial NAT with friendlier numbers. Try it first. A machine turns out items, each one defective with probability 0.1 independently. In a box of 6, what's the chance of exactly 1 defective? It's choose which one is defective, times the probability that 1 is bad, times the probability the other 5 are good. 6 choose 1 is 6. The bad one contributes 0.1. The 5 good ones contribute 0.9 to the 5th power. 0.9 squared is 0.81. To the 4th is 0.6561. Times 0.9 again is 0.5949. Multiply it all. 6 times 0.1 is 0.6. Times 0.5949 is about 0.354, roughly 35%. Choose the positions, then weight by successes and failures. The binomial recipe every time. Continuous variables need a new picture. There are no bars now. Instead, a density curve, and probability is the asterisk area under it. The continuous uniform is a flat rectangle. Every interval of equal width is equally likely. One consequence trips people up. The chance of landing on any exact single value is 0. With continuous things, only ranges have probability. The exponential distribution models waiting times until the next call, the next decay, the next failure. The chance of waiting longer than time t is e to the minus lambda t, and the average wait is 1 over lambda. Its signature is startling. It's memoryless. If a bus arrives on an exponential schedule and you've already waited 10 minutes, your expected remaining wait is exactly the same as when you arrived. The past tells it nothing. Put a number on the waiting. Calls arrive at a rate of 1 every 2 minutes. Lambda is 0.5 per minute. So the mean wait is 1 over 0.5, 2 minutes. What's the chance you wait more than 4 minutes? That's e to the minus lambda times t. Minus 0.5 times 4, e to the minus 2, about 13.5%. The tail of an exponential is a single clean exponential. No integration to grind. Close cousin. The Poisson counts how many rare events land in a fixed interval, calls per minute, typos per page. It has one parameter, lambda, which is both its mean and its variance. When you have many chances and each is unlikely, a binomial quietly becomes a Poisson. That's why it shows up everywhere counts do. 2 calls a minute on average. What's the chance of a silent minute? 0 calls? The Poisson probability of 0 is simply e to the minus lambda, e to the minus 2, about 13.5%. One clean exponential, no factorials to grind. Know the formula, and these are free marks. And the partner question, the chance of us at least 1 month's call in that minute. There's the complement trick again. 1 minus the chance of 0, 1 minus e to the minus 2, about 86.5%. At least 1 almost always means 1 minus none, whether you're rolling dice or counting calls. The same idea keeps paying off across the whole subject. And the queen of distributions, the normal, the bell. Symmetric around its mean, with spread set by its standard deviation. Memorize its fingerprint. About 68% of the mass sits within 1 standard deviation of the mean, 95 within 2, 99.7 within 3. That single fact answers a surprising number of questions on site. Every normal is the same normal in disguise. Subtract the mean and divide by the standard deviation, and any bell becomes asting that bell centered at 0 with spread 1. That number, Z, is just how many standard deviations from the mean. A score of 70 on a test averaging 60 with spread 10 is 1Z, one deviation above. Standardize, then read the table. So scores normal with mean 60, deviation 10. What fraction score below 70? 70 standardizes to Z equals 1. From the Bell's fingerprint, everything below one deviation above the mean is about 84%. No integration, standardize, then look it up. That's the entire technique. And a between question, which is just to Z. The chances score lands between 50 and 70. 50 is one deviation below the mean, Z of -1. 70 is one above, Z of +1. The area between them is the area below +1 minus the area below -1. 84% minus 16%, about 68%, which is exactly the within one deviation rule we just memorized. The fingerprint and the Z table are the same fact, seen two ways. A between question on a fresh Bell. Predict before I reveal. IQ scores are normal, with mean 100 and standard deviation 15. What fraction of people score between 85 and 130? Standardize each edge. 85 is 15 below the mean, so its Z is -15 over 15, -1. 130 is 30 above the mean. Z of 30 over 15 plus 2. The probability between them is the area below +2 minus the area below -1. From the table, below +2 is about 0.977, and below -1 is about 0.159. Subtract. 0.977 minus 0.159, about 0.82, roughly 82%. 2 Z-scores, 2 table lookups, 1 subtraction. That's every between normal question. With 2 variables at once, we use a joint table. The probability of each pair. Sum across a row or down a column, and you recover each variable alone. The marginals, literally written in the margins. And the test for independence becomes mechanical. Multiply the marginals and see if you get the joint cell. If every cell matches, independent. If even one doesn't, dependent. Test 1. A joint table. The 4 probabilities are 0.3, 0.1, 0.2, 0.4. First, the marginals. Sum the top row for x equals 0, that's 0.4. Sum the left column for y equals 0, 0.5. Now the check. If they were independent, the corner cell should be 0.4 times 0.5, 0.2. But the table says 0.3. They disagree, so x and y are dependent. One mismatched cell is enough. You don't have to check the rest. One more idea that returns inside Bayesian networks: conditional expectation. The expected value of something given a condition is just its average within that slice of the world. And the law of total expectation rebuilds the overall mean as the weighted average of those conditional means. 2 machines make parts. Machine A makes 60% of them and averages 10 defects a batch. Machine B makes 40% and averages 20. The overall average is 0.6 times 10, plus 0.4 times 20, 6 plus 8, 14. Average within each case, then average across the cases, weighted by how often each occurs. Condition, then uncondition. Covariance asks, when x is above its mean, is y too? Positive means they rise together. Negative means one falls as the other rises. But covariance's size depends on units, so we normalize it into correlation, pinned between -1 and +1. 2 warnings gate loves. Correlation captures asterisation only. That U-shaped cloud has a strong relationship and a correlation near 0. And correlation is never, by itself, causation. Quick one, 3 points. 1, 2, 2, 4, 3, 6. Every y is exactly twice its x, a perfect line. Grind the covariance if you like, 4/3 using the population divisor, but you already know the answer. Correlation is +1, the maximum, because the points lie exactly on an upward line. Whether you divide by n or n-1, it cancels in the correlation. Perfect line up, +1. Perfect line down, -1. No line, 0. Now the result that makes statistics possible. Take any population at all. Skewed, lumpy, nothing like a bell. Draw a sample, average it. Draw another, average it. Keep going, and watch what the fuck averages asterisk do. The averages pile up into a bell, no matter how strange the original shape was. That's the central limit theorem. The sample means center on the true mean, and their spread, the standard error, shrinks as 1 over the square root of the sample size. Quadruple your sample, and the uncertainty only halves. This is why a normal shows up even when nothing in sight is normal, and why bigger samples are trusted more. A real central limit calculation. A population has mean 50 and standard deviation 10. Take a sample of 25 and average it. How likely is that average to exceed 54? First, the standard error, 10 over the square root of 25, which is 10 over 5, 2. Now standardize the sample mean. 54 is 50 plus 2 standard errors, a Z of 2. The chance of beating to standard deviations is about 2.3%. Notice the spread we used was the standard error, sigma over root n, not sigma itself. That swap is the whole trick of sampling. From the central limit theorem, we build a confidence interval, an estimate with a margin. A 95% interval means this. If you repeated the whole experiment many times, about 95% of the intervals you'd build would contain the true value. It does not mean a single fixed interval has a 95% chance of catching it. The true value isn't random. Your interval is subtle and examined. Build 1. A sample of 36 has mean 100 with population deviation 15. The standard error is 15 over the square root of 36. 15 over 6, 2.5. A 95% interval reaches 1.96 standard errors either side. That's about 4.9. So the interval is 100 plus or minus 4.9. From 95.1 to 104.9. Estimate plus or minus Z times the standard error. That's every confidence interval question. Hypothesis testing is a courtroom for claims. You assume the boring default, the null hypothesis, nothing's going on, and ask, if that were true, how surprising is my data? That surprise is the p-value. Small p means the data would be a shock under the null, so you reject it. The usual bar for too surprising is 5%. 3 tests cover almost everything GATE asks. Comparing means when you know the population spread or your sample is large, use a z-test. When the spread is unknown and the sample is small, the t-test, with its slightly fatter tails. And when your testing counts in categories, is this die fair? Are these two things associated? The chi-squared test. Pick by what you know and what you're measuring. One work decision. A coin shows 60 heads in 100 flips. Is it fair? Assume it is. Then heads count averages 50 with a standard deviation of 5. 60 is 2 standard deviations out, a z of 2, which counting both tails since unfair cuts either way is about a 4.5% two-tailed probability, just under 5. So at the 5% bar, we reject fairness, but only barely. See how the central limit theorem, the normal, and the z-score all just showed up together. That's the subject closing its own loop. And a chi-squared? By hand. Roll a die 60 times. If it's fair, you expect 10 of each face. Suppose you observe 8, 12, 9, 11, 10, 10. The chi-squared statistic adds, for each face, the squared gap from 10 divided by 10. 4, 4, 1, 1, 0, 0. Summing to 10 over 10, a statistic of 1. The critical value with 5 degrees of freedom is about 11. 1 is nowhere near 11, so we fail to reject. The die looks perfectly fair. Small statistic, no evidence of bias. That's all of probability and statistics, end to end. Counting feeds probabilities. Bayes flips them, and the Bayes rate decides the answer. Random variables put numbers on outcomes, summarized by a linear expectation and a variance. A handful of distributions, binomial, exponential, poison, normal, cover most of reality. And the central limit theorem lets us reason from samples to the world, through confidence intervals and tests. 5 pillars, every one now yours. Probability gave us uncertainty in one or two numbers at a time. But real data comes in hundreds of dimensions at once. And to handle that, we need the language of vectors and matrices. That's linear algebra. And it's next. Here's the shift in thinking. A row of data, someone's height, weight, age, income, isn't a list. It's a point in space, an arrow from the origin. 1,000 customers are 1,000 arrows in a high-dimensional room. Linear algebra is how we move, measure, and compress those arrows, and it quietly powers almost every machine learning idea in the second half of this course. Two operations define a vector. Add them tip to tail. Walk along the first, then the second. Scale 1. Stretch or shrink it. Flip it if the scalar is negative. That's it. Combine those two. Scale several vectors and add the results, and you get a linear combination. The single move that this entire subject is built on. Every richer idea, span, basis, transformations, is just adding and scaling, dressed up. The dot product turns two vectors into a single number, and it's secretly about angle. It's the lengths multiplied by the cosine of the angle between them. So when two vectors are perpendicular, the cosine is 0, and the dot product is 0. That's how a computer astro's wish to directions are at right angles. Hold that thought. Orthogonality runs through this entire subject. Let's put a number on it. Take a equals 3, 4, and b equals 4, minus 3. The dot product multiplies matching components and adds. 3 times 4 is 12, plus 4 times minus 3 is minus 12. 12 and minus 12 cancel to 0. A0 dot product means one thing. These two arrows are exactly perpendicular, even though nothing about the numbers looked it. That's the orthogonality test you'll use again and again. Now one where they're not perpendicular, predict the angle before I reveal it. A is 2, 1, B is 1, 3. The dot product is 2 plus 3, 5. The lengths are root 5 and root 10. Cosine of the angle is the dot over the product of lengths, 5 over root 50. Root 50 is 5 root 2, so this is 1 over root 2. And 1 over root 2 is the cosine of 45 degrees. The dot product handed us the angle directly. No protractor needed. Here's a projection as a number. The shadow of one vector on another. Drop B, 4, 2, straight down onto the line through A, 1, 1. The recipe is A dot B over A dot A times A. The top is 4 plus 2, 6. The bottom is 1 plus 1, 2. 6 over 2 is 3. So the shadow lands at 3 times 1, 1. The point 3, 3 on the line. And the bit left over, 1 minus 1, is perpendicular to the line. Check it. It's dot with 1, 1 is 0. Projection splits any vector into along the line, plus at right angles to it. Try this projection yourself before I work it. Drop B, 7, 4, onto the line through A, 3, 1, same recipe. A dot B over A dot A times A. The top is 3 times 7 plus 1 times 4, 21 plus 4, 25. The bottom is 3 times 3 plus 1 times 1, 9 plus 1, 10. 25 over 10 is 5 halves, so the shadow is 5 halves times 3. 1. The point 15 halves, 5 halves, that's 7.5 and 2.5. And the leftover, B minus the shadow, is minus 1 half, 3 halves. Check it's perpendicular, it's dot with 3. 1 is 3 times minus 1 half plus 1 times 3 halves, minus 3 halves plus 3 halves, 0. The shadow plus a right angle remainder. Every projection splits a vector exactly that way. Now the star of the show. Don't think of a matrix as a grid of numbers. Think of it as a machine that transforms space. Feed it a vector. It hands back a moved vector. The whole grid gets rotated, stretched, sheared. The columns of the matrix are simply where the basic unit arrows land. See a matrix. Picture space bending. Let's feed a matrix a vector by hand. A is 2, 0 on top, 1, 3 below. Push through the vector 1, 2. Each output component is a row dotted with the vector. Top row, 2 times 1 plus 0 times 2, that's 2. Bottom row, 1 times 1 plus 3 times 2, that's 7. Out comes the arrow 2, 7. And notice, the columns of A 21 and 03 are exactly where the unit arrows 10 and 01 get sent. Know the columns, and you know the whole machine. Multiplying matrices is doing one transformation after another. Composition. Order matters, because rotating then stretching isn't stretching then rotating. Take the arrow pointing along the x-axis. Stretch it sideways first and then rotate. You get one thing. Rotate it up first and then stretch sideways. You get something taller. Different answers from the same two moves. So a times B is generally not B times A. A few special ones to recognize on sight. The identity leaves space untouched. A diagonal matrix just stretches along the axis, and a symmetric matrix, equal to its own transpose, has especially clean behavior wheel cache-in at eigenvalues. Take some vectors and every possible sum of their scaled copies. That reachable set is their span. Two independent arrows in 3-D sweep out a whole plane. But if a third arrow already lies in that plane, it adds nothing new. It's redundant. Think of 10 and 01 in the flat plane. Together, they already reach every point. Hand me a third vector, say 2, 3. It's just 2 of the first plus 3 of the second. So it stretches the span not one bit. That idea of adds nothing new is the gateway to independence. Before independence, the container itself, a vector space and its subspaces. A subspace is a subset that's self-contained under R2 operations. Add any two of its vectors and you stay inside it. Scale any vector and you stay inside it. One immediate consequence, it must contain the 0 vector, since scaling anything by 0 lands you there. So, is the set of all vectors whose coordinates sum to 0 a subspace of 3D space? Add 2 of them. The coordinates still sum to 0, scale 1, still 0, and the 0 vector itself qualifies. Yes. And geometrically it's a plane through the origin. But change the rule to coordinates sum to 1 and it fails on the spot. The 0 vector isn't in it. Through the origin, closed under combinations. That's the whole subspace test. Vectors are linearly independent when none of them is a combination of the others. No redundancy at all. A basis is the sweet spot. Just enough independent vectors to reach everything. None wasted. And the number of vectors in a basis is the dimension of the space. 2 for a plane, 3 for our world. Independent and spanning. That's a basis. Let's decide independence with a number. Put 2 vectors as the columns of a matrix and take the determinant 0 means dependent. Non-zero means independent. First pair, 1, 2 and 2, 4. The determinant is 1 times 4 minus 2 times 2, 4 minus 4, 0. They're dependent. The second is just twice the first. Second pair, 1, 0 and 1, 1. Determinant is 1 times 1 minus 0 times 1, that's 1, non-zero. Independent. One determinant settles it. Now 3 vectors in 3D. Predict whether they form a basis. Stack 1, 0, 0, 1, 1, 0 and 1, 1, 1 as columns. That's upper triangular. So its determinant is just the product down the diagonal. 1 times 1 times 1, 1. Non-zero. So the 3 are independent. And 3 independent vectors in 3D space reach everywhere. They're a basis, and the dimension is 3. The triangular shortcut turned a 3 by 3 test into a single glance. Here's why a 0 determinant means dependent columns, and it's worth really seeing. The columns of a matrix are arrows, and the determinant is the area of the parallelogram they span. If the columns point in genuinely different directions, that parallelogram has real area. But the moment one column is a multiple of another, dependent, the 2 arrows lie along the same line. The parallelogram flattens to nothing, and the area is 0. Dependence and zero determinant aren't two facts. They're the same fact seen from two angles. To actually compute with this, we reduce. Gaussian elimination sweeps a matrix into a staircase form using row operations. The number of steps in that staircase, the pivots, is the rank. Rank is the real dimension of what the matrix's columns can reach. How much genuine, non-redundant information the matrix carries. Geometrically, rank is how many dimensions survive. Picture a full 3D cloud of arrows pushed through a matrix. A rank 3 matrix keeps it three-dimensional. Nothing is lost. A rank 2 matrix flattens the whole cloud onto a plane. One dimension is gone forever. A rank 1 matrix crushes everything onto a single line. So rank counts the output dimensions, and anything below full rank means the transformation has thrown information away, which, as we'll see, is exactly when it can't be undone. Find the rank of this 3 by 3. Try it first. Rows are 1 to 3, 2, 4, 6, and 1 when 1. Look hard at the second row. It's exactly twice the first, so elimination wipes it out to all zeros. That leaves two independent rows, 1 to 3 and 1 when 1, which don't line up. Two surviving pivots, so the rank is 2, not 3. A full-looking 3 by 3 can quietly be rank 2 when a row hides as a multiple of another. Here's a rank. You can't read off by a single glance. Reduce it yourself. The rows are 1 to 1, 2, 3, 1, and 3, 5, 2. Clear the first column, subtract twice row 1 from row 2, and you get 0, minus 1, minus 1. Subtract 3 times row 1 from row 3, and you get the same, 0, minus 1, minus 1. Those two new rows are identical. So subtract one from the other, and the third row collapses to all zeros. Two pivots survive. Row 1 and 0, minus 1, minus 1. So the rank is 2, not 3. And sure enough, the determinant is 1 minus 2 plus 1, 0, which already told us full rank was impossible. When two rows reduce to the same thing, one of them is dead weight. Here's the theorem that ties it together. Rank plus nullity equals the number of columns. Every column is either a pivot, contributing to rank, or free, contributing to the null space. The directions the matrix crushes to 0. So, if a matrix has more columns than its rank, it must flatten some directions. And the system AX equals 0 has infinitely many solutions. Counting pivots tells you the entire solution structure. Use the theorem on the matrix we just did. Predict its nullity. It had 3 columns and rank 2. Rank plus nullity equals the number of columns. So nullity is 3 minus 2, 1. That one free dimension is a whole line of vectors. The matrix sends straight to 0. It's null space. And because the nullity is bigger than 0, the equation AX equals 0 has not just the trivial solution, but infinitely many. The pivot count alone told us the system's entire fate. Watch how rank decides everything. Two equations. X plus y is 2, and twice that is 4. The second is just the first doubled. The same line, so infinitely many solutions sit along it. But keep the left sides and make the right side 5. Now the lines are parallel and never meet. No solution. Same coefficient matrix. Determinant 0 in both. Singular, and the right-hand side alone flips it between infinite and none. Determinant non-zero would have forced exactly 1. Start with a clean 2 by 2. Predict the crossing point before I solve it. The equations are 2x plus y equals 5 and x minus y equals 1. Here's the trick of elimination. The y terms are plus y and minus y. So just add the two equations and y vanishes. 3x equals 6, so x is 2. Drop that back into x minus y equals 1. 2 minus y is 1, so y is 1. The lines meet at 2, 1. Cancel a variable by combining rows. Solve for one unknown, then back substitute. That's Gaussian elimination in miniature. Now a full 3 by 3 solved to actual numbers. The equations, x plus y plus z is 6, 2y plus 5z is minus 4, and 2x plus 5 y minus z is 27. Subtract twice the first row from the third to kill x, then chase the variables down. Working back up, z comes out minus 2, then y is 3, and x is 5. Predict check yourself. 5 plus 3 minus 2 is 6. The first equation holds. Gaussian elimination always lands you on a definite triple when the determinant isn't 0. The determinant measures how a transformation scales area or volume in higher dimensions. A determinant of 3 triples areas, a determinant of 1/2 halves them. And the critical case. When the determinant hits 0, space collapses onto a lower dimension, a line or a point, and the transformation can't be undone. For a 2 by 2, it's simply AD minus BC. A 3 by 3 determinant by cofactor expansion. Pause and try the first minor yourself. Take A as 123 on top, 045, then 106. Expand along the top row with the sign pattern plus, minus, plus. The first term, 1 times the little determinant 4506, which is 24, minus 2 times 0516, which is 0 minus 5, minus 5. So minus 2 times minus 5 is plus 10, plus 3 times 0410, which is minus 4, giving minus 12. Add 24 plus 10 minus 12 is 22. Cross out a row and a column. Take each little determinant, alternate the signs. That's the whole method. The inverse is the undo button. Apply A, then A inverse, and you're back where you started. But you can only undo a transformation that didn't lose information. So a matrix is invertible exactly when its determinant is non-zero, which is exactly when it has full rank. Singular, zero determinant, rank deficient, non-invertible. In this subject, those are 4 names for the same situation. Let's invert a 2 by 2 by formula. A is 2111. Step 1. The determinant. 2 times 1 minus 1 times 1. That's 1. Non-zero. So it's invertible. The 2 by 2 inverse swaps the diagonal entries, negates the off-diagonal pair, and divides by the determinant. Swapping gives 2 and 1 on the diagonal. Negating the off-diagonals gives minus 1 and minus 1. Divide by 1 and you're done. The inverse is 1, minus 1, 2. Multiply it back against A and you land on the identity. Undo confirmed. One more inverse. Predict the determinant before you trust the formula. A is 435, 4. The determinant is 4 times 4 minus 3 times 5, 16 minus 15, 1. A non-zero 1, so it inverts cleanly. Now the recipe. Swap the diagonal entries, negate the off-diagonal pair, divide by the determinant. Swapping the diagonal leaves 4 and 4. Negating the off-diagonals gives minus 3 and minus 5. And dividing by 1 changes nothing. So the inverse is 4. Minus 3, minus 5, 4. Multiply it back. Top left is 4 times, 4 plus 3 times, minus 5. 16 minus 15, 1. Bottom right is 5 times minus 3 plus 4 times 4. Minus 15 plus 16, 1. The identity. A determinant of 1 makes the inverse all integers, which is exactly why Gate picks matrices like this. Push a random arrow through a matrix, and it usually comes out pointing somewhere new, rotated and stretched. But hidden inside almost every square matrix are a few special directions that don't turn at all. They only get longer or shorter, staying exactly on their own line. Those unturned directions are the eigenvectors, and how much they stretch is the eigenvalue. They matter because along those directions, the matrix acts like plain multiplication by a number, which is as simple as a transformation ever gets, and applying it many times just raises that number to a power. That's the lever PCA pulls later. Find the directions a data matrix stretches the most. In symbols, a times the special vector v equals just a number lambda times v. Same direction, rescaled. To find them, rewrite it as a minus lambda times identity. Hitting v gives 0. For a non-zero v to be crushed to 0, that matrix must be singular. Its determinant must vanish. Set that determinant to 0, and you get the characteristic equation, whose roots are the eigenvalues. Let's solve one. Take the symmetric matrix 2 1 1 2. Its characteristic equation is lambda squared minus 4 lambda plus 3 equals 0, and that factors to lambda equals 1 and lambda equals 3. The direction 1, 1 gets stretched by 3. The perpendicular direction 1, minus 1 is stretched by 1. To clean real eigenvalues, symmetric matrices always oblige like that. Here's a gift Gate loves to hand out. Read these eigenvalues off by sight. The matrix is upper triangular, 271, then 053, then 009, with everything below the diagonal 0. For any triangular matrix, the determinant of a minus lambda is just the product of the diagonal minus lambda. So the eigenvalues are exactly the diagonal entries, 2, 5, and 9. Those 7, 1, and 3 of the diagonal are pure decoration. Spot a triangular matrix and you've already won. Verifying an eigenvector is faster than finding one. Predict whether 1 works for this AA is for 1 to 3. Multiply by the vector 1, 1. Top row 4 plus 1 is 5. Bottom row 2 plus 3 is 5. Out comes 5, 5, which is exactly 5 times 1, 1. Same direction, scaled by 5. It is a weight in vector. Eigenvalue 5. Try 1, minus 2 as well. Ascends it to 2, minus 4, which is 2 times 1, minus 2, eigenvalue 2. To check a claimed eigenvector, just multiply and see if the answer is a clean multiple of the original. 2 shortcuts to memorize. They save whole questions. The trace, the sum down the diagonal, always equals the sum of the eigenvalues. And the determinant always equals their product. Check our example. Trace 4 equals 1 plus 3. Determinant 3 equals 1 times 3. If a problem gives you a trace and a determinant, you may already know the eigenvalues without solving anything. For any 2 by 2, you can write the characteristic equation without expanding a determinant. Predict it from trace and det. The rule: lambda squared minus the trace times lambda plus the determinant. Take her as 5, 4, 1, 2. The trace is 5 plus 2, 7, and the determinant is 5 times 2 minus 4 times 1, 10 minus 4, 6. So the equation is lambda squared minus 7 lambda plus 6 equals 0. The discriminant is 49 minus 24, 25, whose root is 5. So lambda is 7 plus or minus 5 over 2, giving 6 and 1. Trace and determinant build the whole quadratic for you. Your turn on a fresh symmetric 2 by 2. Find both eigenvalues. M is 3226. Use the shortcuts. The trace is 3 plus 6, 9, and the determinant is 3 times 6 minus 2 times 2, 18 minus 4, 14. So the characteristic equation is lambda squared minus 9 lambda plus 14 equals 0. Factor it. What two numbers add to 9 and multiply to 14? 2 and 7. So the eigenvalues are 2 and 7. Sanity check with the same two shortcuts. 2 plus 7 is 9, the trace, and 2 times 7 is 14, the determinant. Both match, so the answer is locked, and because the matrix is symmetric, those real eigenvalues were guaranteed from the start. 2 traps Gate sets here. First, a perfectly real matrix can have complex eigenvalues. 2, minus 1, 3. 1 gives a discriminant of minus 11. The eigenvalues are a complex pair. A real matrix does not guarantee real eigenvalues unless it's symmetric. Second, eigenvectors are never unique. Double 1, and it still points the same way and still works. Don't get thrown when your answer differs from the key by a scale factor. Some transformations don't distort at all. They rotate or reflect, keeping every length and angle intact. Those are orthogonal matrices, and they have a gorgeous property. Their transpose is their inverse. Q transpose times Q is the identity. Their columns are mutually perpendicular unit vectors, and their determinant is plus or minus 1. Rigid motions of space, nothing stretched. Why is an orthogonal matrix's determinant always plus or minus 1? Predict the sign for each of these. A pure rotation has columns cosine sign and minus sign cosine. Its determinant is cosine squared plus sine squared, And that's just 1 always. A reflection, flipping the y-axis with 1, 0, 0, minus 1, has determinant 1 times minus 1, minus 1. Plus 1 means the transformation rotates without flipping. Minus 1 means it reflects, reversing orientation. Either way, the size is 1, because orthogonal maps never stretch or shrink area at all. The syllabus pairs projection with orthogonalization, turning a skewed set of directions into a clean perpendicular one. The Gram-Schmidt process does exactly that. Keep the first vector, then from the second subtract its shadow, its projection, onto the first, and whatever's left is perpendicular to the first. Take 1, 0 and 1, 1. Keep 1, 0. The projection of 1, 1 onto 1, 0 is 1, 0. So subtract it. 1, 1 minus 1, 0 leaves 0, 1. And 0, 1 is exactly perpendicular to 1, 0. Normalize each to length 1, and you've built an orthonormal basis out of a skewed one. Orthogonalization is just projection, turned into a tool. A projection casts a vector's shadow onto a line or plane, the closest point on it. Its signature equation is idempotence. P squared equals P. Projecting once lands you on the subspace. Projecting again does nothing. You're already there. This isn't abstract. It's exactly how least squares regression finds the best fitting line, by projecting the data onto what the model can represent. Linear algebra meets machine learning, right here. Let's make idempotence concrete. The matrix that projects onto the x-axis is 1, 0 on top, 0, 0 below. It keeps the first coordinate and zeros the second. Feed it 4, 7, and you get 4, 0. The point's shadow on the x-axis. Now square the matrix. P times P is still 1, 0, 0, 0. Exactly P again. So projecting a second time does nothing, because 4, 0 is already on the axis. That P squared equals P is the fingerprint of every projection, and it's what makes least squares the closest point, rather than some moving target. A quadratic form feeds a vector into x transpose x and gets a number, and its shape is a landscape. When all eigenvalues are positive, it's a perfect upward ball. Positive definite. One lowest point. Mixed signs give a saddle. This is precisely the landscape an optimizer descends. So, positive definite is the linear algebra way of saying this has a single friendly minimum, which we'll need the moment we train models. A fast positive definite check. Predict which of these two passes. Sylvester's rule says the leading minors, the determinants of the top left 1 by 1, 2 by 2, and so on, must all be positive. First matrix, 2, 1, 1, 2. The top left entry is 2, positive, and the full determinant is 4 minus 1, 3, positive. All leading minors positive. Positive definite, a genuine ball. Second matrix, 2, 1, 1 minus 1. Top left is 2, fine, but the determinant is minus 2 minus 1, minus 3, negative. One negative minor kills it. Not positive definite, that's a saddle. You never had to find a single eigenvalue. One more, a 3 by 3 that shows up everywhere. The tridiagonal 2, minus 1 matrix. 2 on the diagonal, minus 1 just off it, zeros in the corners. Leading minors. The first is 2, positive. The 2 by 2 top left is 4 minus 1, 3, positive. And the full 3 by 3 determinant works out to 4, positive. 3 for 3, positive definite. Equivalently, all its eigenvalues are positive. But climbing the leading minors got us there, without solving a cubic. One workhorse factorization. Gaussian elimination. The staircase process can be recorded as a product. A equals L times U, a lower triangular matrix times an upper triangular one. The U is the staircase you end up with. The L quietly stores the multipliers you used to get there. Why bother? Because once you've paid for the factorization, you can solve the system for many different right-hand sides cheaply. Solve with the lower triangular L, then with the upper triangular U, each a quick sweep. It's elimination, bottled for reuse. And the crown jewel, the singular value decomposition. It says shit any should matrix. Even a non-square one is secretly just three simple moves. A rotation, then a pure stretch along the axis, then another rotation. Watch a circle of vectors go in, get spun, stretched into an ellipse, and spun again. The stretch amounts are the singular values. The matrix's true scale factors, always real and non-negative. The singular values come ordered, biggest first, and they rank importance. Keep the few largest, and you capture most of the matrix with a fraction of the numbers. That's compression, that's noise removal, and as we'll see, that's the engine inside PCA. The biggest singular directions are where the data truly lives. The tiny ones are mostly noise you can throw away. A clean fact they test. The number of non-zero singular values is exactly the rank of the matrix. Those are the directions that survive, not collapse to zero. And for a symmetric positive matrix, the singular values and eigenvalues coincide. SVD generalizes the eigenidea to every matrix, which is why it's the bridge from pure linear algebra into data. Tie it back to rank with a quick read. Suppose a 3 by 3 matrix has singular values come out as two positive numbers and then a 0. Predict its rank. The count of non-zero singular values SP is the rank. 2 non-zero here. So rank 2. That third singular value being 0 means one whole dimension got crushed flat. The same crushed direction we called the null space earlier. Rank, nullity, determinant 0, and a 0 singular value. All of them are the same collapse, described in 4 different dialects of this one subject. That's linear algebra. Data points are vectors. The dot product measures angle and spots right angles. Matrices transform space. Rank tells you how many dimensions survive, and so how many solutions a system has. The determinant scales area and flags the singular, uninvertible case. Eigenvectors are the directions a matrix doesn't rotate, with the trace equals sum and determinant equals product shortcuts. And the singular value decomposition reveals any matrix as a rotate stretch rotate. Every one of these returns inside machine learning. We can now move and measure data in any number of dimensions. The next question is how things best change and how we find the best possible answer by following a slope downhill. That's calculus and optimization. Two ideas deeply linked. Calculus is the mathematics of change, how fast something moves at an instant. Optimization is finding the best, the highest profit, the lowest error. And they meet at one beautiful fact. The best place is usually where the slope goes flat. Every model you train later is a ball rolling downhill to the bottom of an error curve. This is that machinery. First, the object itself. A function is a machine. One input goes in. Exactly one output comes out. That exactly one is the whole rule. Feed it the same input twice, and it must hand you back the same answer twice. Its graph is the picture of every input-output pair at once. The inputs it accepts are the domain. The outputs it can produce are the range. Simple but worth saying clearly, because every limit, derivative, and optimum in this chapter is just a statement about this one curve. A limit asks, as the input creeps towards some value, where is the output heading? Crucially, not where it pokes, is wonder. The function can even have a hole at that point and still have a perfectly good limit, because the limit is about the approach, not the arrival. And here's the catch that decides existence. You must approach from bits tides. If the left-hand approach and the right-hand approach head to the same place, the limit exists. If they disagree, say one side dives to minus infinity and the other climbs to plus infinity, like 1 over x at 0, the limit simply does not exist. Both sides must agree. Most exam limits arrive looking like 0 over 0, undefined on the surface. The trick is algebra. Take x squared minus 1 over x minus 1 at x equals 1, top and bottom both vanish. But factor the top into x plus 1 times x minus 1, Cancel the common piece, and you're left with simply x plus 1, which heads to 2. The 0 over 0 was a removable disguise. Your turn, same idea, fresh numbers. The limit, as x approaches 3, of x squared minus 9 over x minus 3. Pause and predict. Plug 3 in blindly, and you get 0 over 0 again. But x squared minus 9 is a difference of squares. It factors into x minus 3 times x plus 3. The x minus 3 on top cancels the 1 on the bottom, leaving just x plus 3. Now substitute 3. 3 plus 3 is 6. Spot a difference of squares, and these collapse instantly. Now a limit where factoring alone won't help, but rationalizing will. The limit, as x approaches 4, of root x minus 2 over x minus 4. Both top and bottom go to 0. The move here is to multiply top and bottom by the conjugate, root x as plus 2 on top. Root x minus 2 times root x plus 2 is just x minus 4, which cancels the denominator perfectly. You're left with 1 over root x plus 2. Put in 4. 1 over root 4 plus 2, 1 over 2 plus 2, 1 quarter. When you see a square root sitting in a 0 over 0, reach for the conjugate. A different flavor of limit, not at a point, but at infinity. The limit, as x runs off to infinity, of 3x squared plus 2x over x squared minus 5. The clean move is to divide every single term by the highest power, x squared. On top, you get 3 plus 2 over x. On the bottom, 1 minus 5 over x squared. Now let x grow without bound. 2 over x dies away to 0, and 5 over x squared dies even faster. What survives is 3 over 1, 3. The shortcut worth remembering: when top and bottom have the same degree, the limit at infinity is simply the ratio of their leading coefficients. When factoring won't crack it, L'Hopital's rule is the power tool. For a genuine 0 over 0 or infinity over infinity, you may differentiate the top and the bottom separately, and try the limit again. 1 minus cosine x over x squared becomes sine x over 2x, still 0 over 0. So again, cosine x over 2, which settles at 1/2. Differentiate, retry, repeat, until it resolves. Another for the toolkit. The limit, as x approaches 0, of e to the x minus 1 over x. At 0, the top is 1 minus 1, 0, and the bottom is 0. Fair game for L'Hopital. Differentiate the top. The derivative of e to the x is e to the x. Differentiate the bottom. The derivative of x is 1, so the ratio becomes e to the x over 1. And at 0, that's e to the 0, exactly 1. This little limit is secretly the slope of the exponential at the origin, which is why it equals 1. A classic, predict it. The limit of sine x over x as x approaches 0. Pause. It's a 0 over 0, but the answer is exactly 1. Near 0, sine x and x are almost the same line, so their ratio hugs 1. This single limit is the seed of why the derivative of sine is cosine, and it shows up constantly. Worth knowing cold. A function is continuous if you can draw it without lifting your pen. No holes, no jumps, no blow-ups. Formally, 3 things must agree, all at the same point. The function is actually defined there, the limit exists there, and the value and the limit are equal. A hole breaks the first, a jump breaks the second, and a removable mismatch breaks the third. Break any one of the 3, and you have a discontinuity. Continuity is the well-behaved baseline everything else builds on. Here's how gate turns continuity into a number. A piecewise function. It's x squared up to x equals 2, and a times x plus 1 beyond 2. For what value of a does it join smoothly, with no jump? The rule is that the 2 pieces must meet at the seam. From the left, at 2, x squared is 4. From the right, a times 2 plus 1. Set them equal. 4 equals to a plus 1. So 2a is 3, and a is 3 over 2. Match the pieces at the boundary. That's the whole technique. The derivative is just slope, made instantaneous. Draw a line through two nearby points on the curve. That's a secant, an average rate of change between them, and slide the 2 points together until they merge into one. The line you're left with is the tangent, and its slope is the derivative. It's the exact rate of change at that single instant. How steep the curve is, right there. Positive slope means the function is rising, negative means it's falling, and zero means, for a moment, it's perfectly flat, which is exactly the clue optimization will hunt for. Now a trap gate genuinely loves. Differentiable always implies continuous, but the reverse fails. Take the absolute value function at 0. It's perfectly continuous, no gap at all, but it has a sharp corner. Approach the slope from the left and it's -1, from the right, +1. No single tangent exists. So a function can be continuous yet not differentiable, exactly at its corners. Smoothness is stronger than mere connectedness. Push it one level harder. Make the join not just continuous, but smooth-mouthed. No corner. Same template. X squared up to 1. Then ax plus b. Two conditions now. First, the values must match at 1. 1 equals a plus b. Second, the asterisk slopes must match. The derivative of x squared is to x, which is 2 at x equals 1. So a must be 2. Back substitute. If a is 2, then b is 1 minus 2, minus 1. Two equations because we demand two things. Continuity asterisk, a matching slope. A few rules differentiate anything. The product rule for things multiplied, the quotient rule for things divided, and the most important of all, the chain rule for a function inside a function. You differentiate the outer, keep the inner, then multiply by the inner's derivative. Remember the chain rule especially. Stacked, nested functions are exactly what a neural network is, and the chain rule backpropagation. You're meeting it here first. Why does the chain rule Vettis multiply as to? Picture two meshed gears. Turn the crank, and the inner gear spins 3 times as fast. That's the inner derivative. The outer gear spins twice for every turn of the inner. That's the outer derivative. So how fast does the final gear move when you crank once? 3 times 2, 6. The rates compound. That's all the chain rule is. A nested function passes its rate of change down the line, and to get the overall rate you multiply the links together. Stack many gears, and you get backpropagation through a deep network. Chain rule in action. Differentiate sine of x squared. The outer function is sine, whose derivative is cosine. So cosine of x squared. Then multiply by the derivative of the inside, x squared, which is 2x. Put together, 2x times cosine of x squared. Outer first, then times the inside's derivative. That rhythm handles every nested function they can throw at you. Now both rules at once. The kind of composite gate actually sets. Differentiate x squared times sine of 3x. It's a product. So the product rule first. Derivative of x squared, which is 2x, times sine 3x, plus x squared times the derivative of sine 3x. That last derivative needs the chain rule. The outer sine gives cosine 3x, then times the derivative of the inside, 3x, which is 3. Collect it all. 2x sine 3x plus 3x squared cosine 3x. Product on the outside, chain on the inside. Layer them and nothing is too tangled. Taylor series is a superpower. Approximate any smooth function near a point with a polynomial using its derivatives. One term gives the tangent line, 2 terms add curvature, and each extra term hugs the true curve more tightly. E to the x, for instance, is 1 plus x squared over 2 and onward. This is how calculators compute, and how we linearize hard functions to make them tractable. Let's turn that series into a number. Approximate e to the 0.1 using just 3 terms. 1 plus x squared over 2. Put x equal to 0.1. 1 plus 0.1 plus 0.1 squared over 2. That's 0.005. Add them. 1.105. The true value is 1.1052 and change. So 3 terms already kneel it to 4 decimal places. That's the power of Taylor. A few derivatives and a hard exponential becomes simple arithmetic. Before we optimize, one subtle truth that trips up the careless. A peak or a valley must have zero slope. You can't be at the very top while still climbing. So zero slope is puck necessary star. But it is not sufficient star. Look at the third flat spot. The curve pauses, goes momentarily horizontal, then keeps right on rising. A flat inflection, neither a max nor a min. So setting the derivative to 0 only gives you fuck candidate star. You still have to check each one. Necessary, not sufficient. Hold that distinction. So to optimize, hunt for those flat spots. A critical point is where the derivative is 0. The slope goes momentarily horizontal. Between them, the sign of the derivative tells the story. Positive, and the function climbs. Negative, and it falls. So the function can only switch from rising to falling, or back, at a critical point. Those are your only candidates for a peak or a valley. But is a flat spot a peak or a valley? The second derivative decides. It measures curvature. Curving upward, like a ball, second derivative positive, a local minimum. Curving downward, like a dome, a local maximum. If the second derivative is also 0, the test is inconclusive, and you fall back to checking the slope on either side. Slope finds the candidates. Curvature classifies them. But what's fishing in derivative really? The first derivative is the slope. The second derivative is the rate of change shut of that slope. How fast the steepness itself is turning. Picture the tangent arrow as you walk along the curve. In a ball, the slope swings from falling to rising. Its patching increases as so. So the second derivative is positive. On a dome, the slope swings the other way, it decreases. So the second derivative is negative. That's the geometry behind the test. Curvature is just the slope of the slope. Work it through on x cubed minus 3x. The derivative, 3x squared minus 3, is 0 at x equals plus and minus 1, 2 critical points. The second derivative is 6x. At x equals 1 it's positive, a local minimum where the function is minus 2. At x equals minus 1 it's negative, a local maximum where the function is plus 2. 2 lines of algebra, fully classified. Here's optimization as a real-world problem, the gate favorite. You have 20 meters of fence and want to enclose the largest rectangle. If one side is x, the perimeter 20 fixes the other side at 10 minus x, because the two sides must sum to half the perimeter 10. So the area is x times 10 minus x. That's 10x minus x squared. Differentiate. 10 minus 2x. Set it to 0 and x is 5. The second derivative is minus 2. Negative? So it really is a maximum. Both sides come out to 5, a square, and the area is 25 square meters. Of all rectangles with a fixed perimeter, the square wins. Translate the words into a function, then optimize. Here's the mistake that costs marks. On a closed interval, the global maximum or minimum might not sit at a critical point at all. It can live at an endpoint. So the rule is strict. Evaluate the function at every critical point check and asterisk at both ends. Then compare. Take our cubic on minus 2 to 3. The critical points give plus 2 and minus 2. The left end, minus 2, gives minus 2. But the right end, x equals 3, gives 3 cubed minus 9. 27 minus 9, 18. 18 towers over every interior value. The global maximum isn't at any flat spot. It's at the endpoint, and it wins outright. Never, ever skip the endpoints. Now you run the full procedure. Take g of x equals to x cubed minus 3x squared minus 12x plus 5 on minus 2 to 3. First, the derivative 6x squared minus 6x minus 12, which factors as 6 times x minus 2 times x plus 1. So critical points at x equals -1 and x equals 2, both inside the interval. Now build the candidate table. At -1, g is 12. At 2, g is -15. At the left end -2, g is 1. At the right end 3, g is -4. Compare all four. The biggest is 12. The smallest is -15. So here both the global maximum and the global minimum land at interior critical points. The lesson isn't, the answer is always at an endpoint. It's check everything, then compare. One last idea that pays off all course. A function is convex if it curves upward everywhere. A single smooth ball. Second derivative never negative. Convex functions are an optimizer's dream because they have no false valleys. Any local minimum you find is fucked global minimum. Guaranteed. That's exactly why we design machine learning loss functions to be convex. When we can, it means rolling downhill actually reaches the best answer, not a trap along the way. How do you actually prove which something is convex? Check the sign of the second derivative. Take e to the x. Its second derivative is e to the x again, which is always positive. So the exponential is convex everywhere. One unbroken ball. Now contrast x cubed. Its second derivative is 6x, which is positive when x is positive, but negative when x is negative. So x cubed is convex on the right half, concave on the left, and it flips exactly at 0, an inflection point. Convex where the second derivative is non-negative. That single test settles it. Calculus, locked in. Limits are about where a function heads, not where it sits. Factor, rationalize, or call in L'Hopital when it's 0 over 0. The derivative is instantaneous slope, and the chain rule will become backprop. To optimize, find where the slope is 0. Necessary, not sufficient. Classify with curvature, and on a closed interval, never skip the endpoints. And convexity guarantees the bottom you find is the true bottom. We've handled the mathematics, uncertainty, dimensions, and change. Now we teach the machine to buck something with it. Next is programming, data structures, and algorithms. Thinking in steps and counting their cost. This section is less about writing code and more about tech reading Morchin. Gate asks two questions over and over. 1. Trace this code by hand. What does it print? 2. How does its running time grow as the input grows? Master careful tracing and the language of cost, big O, and this whole quarter of the paper becomes mechanical. Python first, exam style. Indexing starts at 0, and negative indices count from the end. Slicing takes a start, a stop that's excluded, and an optional step. So 1:3 grabs positions 1 and 2, not 3. A step of -1 reverses. And the rule that drives trick questions. Strings and tuples are immutable. You can't change them in place, while lists and dictionaries are mutable. That mutability is where bugs and exam traps live. Predict before I reveal. The string is ALGORITHM, 9 letters, indices 0 through 8. What is S2:6? Start at index 2, stop visions 2, 3, 4, 5, G, O, R, I. That's Gori. The stop index is never included. That off by 1 is the whole game. What is S with step -1? The full string reversed. MHTIROGLA. And S with empty step 2 takes every second letter from the start. Index 0, 2, 4, 6, 8, A, G, R, T, M, agreed. Slicing is just start, stop excluded, step. Get those 3 and no slice can surprise you. Lists, tuples, dictionaries, sets. Know their behavior. The subtle one, assigning a list to a new name doesn't copy it. It makes a second label for the asterisk same object. Change it through one name and the other sees the change too. To actually copy, you slice or copy explicitly. Dictionaries and sets are built on hashing. So membership tests are effectively instant. A fact we'll formalize soon. Let's trace the trap directly. On the left, A is the list 1, 2, 3. Then B equals A. No copy, just a second sticky note on the bust same shortlist. So when B appends 4, and we print A also shows 1, 2, 3, 4. One list, two names. On the right, X is 1, 2, 3. But Y equals X colon, a slice, which builds a brand new list. Now changing Y's first element to 99 leaves X untouched at 1, 2, 3, while Y is 99, 2, 3. The question is always, are these two names the same object or copies? Plain assignment shares, slicing copies. The most infamous Python trap and a gate favorite. Give a function a default argument that's a list, and that list is created fuck once as calls, not every call. So it secretly remembers across calls, growing each time. The fix is to default to none and build a fresh list inside, and name resolution follows ELGB, local, enclosing, global, built-in. Python searches outward through those scopes. Know both, and the what does this print questions stop surprising you. Worked because the answer shocks people. The default list is built one time, when the function is defined, and every call that doesn't pass its own list reuses that exact same one. So f of 1 appends 1 and returns the list 1. F of 2 appends to the asterisk same short list. Now 1, 2. F of 3 gives 1, 2, 3. The list never resets, because the default was never recreated. If the intended answer were a fresh list each time, the default would have to be none with the list built inside. Spot a mutable default, a list or dictionary, after an equals in the signature, and expect this exact accumulation. Your turn, and this one catches almost everyone. There's a global count equal to 0. Inside inc, we write count equals 1 and return it. What does print inc? Count show. The call returns 1, but the global count is still 0. Why? The moment a function assigns hollers to a name, Python treats that name as local to the function, a separate variable that shadows the global. So inc cheese count and the outer count are different boxes. Changing the inner one leaves the outer at 0. The answer is 1, then 0. To actually modify the global you'd need the keyword global. Assignment creates a local bat. Single rule resolves a whole family of ELGB questions. Recursion is a function that calls itself on a smaller piece, with a base case to stop. Picture factorial of 4. It waits on factorial of 3, which waits on 2, down to factorial of 1, the base case, which returns 1. Then the answers multiply back up the chain. 1, 2, 6, 24. To trace recursion, follow the calls batting down to the base, then resolve what? Backup star, down then up. Trace this one yourself before I reveal. The function returns n for 0 or 1. Otherwise, the sum of the two previous calls, Fibonacci. F of 5. Pause and walk the tree. F of 5 is F4 plus F3. And unrolling it all the way down, the answer is 5. Notice the same subcalls repeat. That wasteful recomputation is exactly why this naive version is exponentially slow, which brings us to cost. How do we compare algorithms fairly across machines and languages? We ignore the hardware and ask only, as the input grows, how does the work grow? That's big O, a statement about the tank shape of the growth curve. We drop constant factors and keep only the fastest growing term, because for large inputs, that term is all that matters. Here's the ladder, best to worst. Constant time, independent of input. Logarithmic, it halves the problem each step, gloriously slow growing. Linear, one pass. Linear times log, the good sorts. Quadratic, a loop inside a loop. And exponential, doom, doubling with every added element. Read the loops, One loop over n is linear, a nested loop is quadratic, and a loop that 10 halves second each time is logarithmic. Count the operations exactly, then name the big O. First loop, the inner runs 0 times when I is 0, 1 time when I is 1, up to n minus 1 times. So the total is 0 plus 1 plus 2, all the way up, which is n times n minus 1 over 2. That's a triangle of work, and dropping the constant 1/2 and the lower term, it's order n squared. Even though the inner loop doesn't run the full n each time, half of a square is still a square. Second loop, I starts at 1 and fuck doubles until it reaches n. So it runs log base 2 often times. Doubling up to n or halving down from n both give a logarithm. Count first, then strip constants. That's how you turn a snippet into a complexity. Two recurrences cover most of what they ask. If a problem halves itself and does constant work each level, that's binary search. The total is logarithmic. If it splits into two halves and does linear work to combine them, that's merge sort. The total is n log n. Memorize these two patterns. You'll recognize them instantly instead of deriving them under pressure. When a recurrence isn't one of the two famous ones, the master theorem decides it in one comparison. Write it as a subproblems, each of size InnoVerb plus order n to the d work to combine. Compute log base b of a and compare it to d. If d equals that log, the work is balanced across levels, and you get n to the d times log n. Merge sort. A is 2, b is 2, d is 1. Log base 2 of 2 is 1, which equals d. So n log n, exactly as we found. If d is 1 smaller is joint than the log, the leaves dominate. Take 4 subproblems of half size with linear combine. Log base 2 of 4 is 2, bigger than d of 1. So the answer is n squared. And if d is wish dense larger than the log, the top level dominates. 3 half-size subproblems with n squared combine. Log base 2 of 3 is about 1.6, less than 2. So n squared again, this time from the root. 1 log, 1 comparison, 3 outcomes. Leaves win, tie, or root wins. Let's run the master theorem on a fresh recurrence. It hasn't seen t of n equals 8t of n over 2 plus order n squared. Read the three constants straight off. A, the number of subproblems is 8. B, the shrink factor is 2. And D, the exponent on the combined work is 2. Now the one comparison, log base 2 of 8. 2 to the third is 8, so that logarithm is 3. Compare it to D, which is 2. 3 is asterisk bigger asterisk than 2, so the log wins, which means the leaves dominate. There are so many subproblems that the bottom of the tree does the most work. When the leaves dominate, the answer is n raised to that logarithm, n to the 3. So 8t of n over 2 plus n squared is order n cubed. Notice the combined cost. N squared never makes it into the final answer at all. It's drowned out by the sheer number of leaves. That's the leaves win case. Count the subproblems, and they decide it. Concretely, a loop that keeps halving n until it reaches 1, starting from 1024. How many times does it run? 10. Because 1024 halved 10 times reaches 1, and that's log base 2 of 2024. Whenever you see the input getting cut by a constant factor each step, think logarithm, and the answer is a count of halvings. One trap. An algorithm has different costs in different cases. Linear search is constant time if your target is first, but linear if it's last or missing. Quicksort averages a beautiful n log n, but on already sorted input with a bad pivot, it degrades to quadratic. So when a question asks for complexity, check case to which age case, best, average, or worst they mean. Conflating Quicksort's average with its worst is a classic lost mark. Searching, two ways. Linear search just scans everything. Simple, works on any list, linear cost. Binary search is far faster but demands a sorted happy. Check the middle, and since it's sorted, Throw away half the list every comparison. Logarithmic time. The catch they test? Binary search is only valid on sorted data, unsorted. And you must either sort first or scan linearly. Let's count binary search steps on a real array. The numbers 1 through 16, sorted, 16 of them, looking for 11. Step 1. The middle is index 7, value 8. 11 is bigger, so discard the left half and everything up to 8. Step 2. The middle of the rest is index 11, value 12. 11 is smaller, discard the right. Step 3. Middle is index 9, value 10. 11 is bigger, go right. Step 4. Index 10, value 11, found. 4 comparisons and 4 is exactly log base 2 of 16. Every step halves what's left, which is asterisk the cost is logarithmic. The halving recurrence T of n equals T of n over 2 plus constant, made concrete. The simple sorts are all quadratic, but they differ. Bubble sort repeatedly swaps neighbors out of order. Selection sort repeatedly grabs the minimum and places it. Insertion sort builds a sorted prefix one card at a time, and it's special. On nearly sorted input, it's nearly linear, which is why it's used as a finisher. Quadratic in general. But insertion has a friendly best case. Trace one bubble pass on 5, 2, 8, 1, 9, 3. Compare the first pair, 5 and 2. Out of order, swap. Giving 2, 5. Next, 5 and 8. Fine, leave them. 8 and 1. Swap. So 1 moves left. 8 and 9. Fine. 9 and 3. Swap. After one full pass, the array is 2, 5, 1, 8, 3, 9. And notice the largest element, 9, has bubbled asked all the way to the last position. That's guaranteed every pass. 3 swaps happened here. 1 pass plants 1 element. That's why bubble sort needs about n passes. And the work is order n squared. Now insertion sort on the same array. Predict each snapshot. We grow a sorted prefix on the left and insert each next card into place. Start. Take 2. Slide it before 5. 2, 5, 8, 1, 9, 3. Take 8. It's already after 5. Stays put. Take 1. It slides all the way to the front. 1, 2, 5, 8, 9, 3. Take 9. Already in place. Finally take 3. Slide it past 8 and 5 to sit after 2. 1, 2, 3, 5, 8, 9. Done. Each element only travels left until it meets something smaller. So on. Near lisorted data, the slides are tiny, and it runs close to linear. Insertion's famous best case. Now selection sort, a different simple sort, traced on a fresh array, 29, 10, 14, 37, 13, 8. The rule each pass. Scan the whole unsorted part, find the smallest, and swap it into the front position. Pass 1. Scan all 6. The minimum is 8 at the very end. Swap it with the 29 in front. The array becomes 8, 10, 14, 30, 7, 13, 29. And that leading 8 is now locked. Pass 2. Scan the remaining 5 from 10 onward. The smallest is 10, and it's already sitting in place. So no swap happens, yet the pass still cost a full scan. Pass 3. Scan from 14 onward. The smallest left is 13. Swap it with the 14, giving 8, 10, 13, 37, 14, 29. Here's the signature of selection sort. It always scans the entire remaining suffix to find each minimum. So it does the same, roughly n-squared comparisons no matter how the data starts. There's no friendly best case like insertions. But it makes at most 1 swap per pass. So when swapping is expensive, selection sort is the frugal choice. Merge sort is divide and conquer. Split the array in half. Sort each half recursively down to single elements. Then merge the sorted halves together. That merging is linear per level. with login levels. N-login, guaranteed in every case. It's stable, preserving the order of equal keys, but it needs extra memory for the merge. Reliable and predictable. The heart of merge sort is the merge. Let's trace just that. Suppose the two halves are already sorted. Left is 2, 5, 8. Right is 1, 3, 9. Put a finger on the front of each and repeatedly take the smaller. Compare 2 and 1, take 1. Compare 2 and 3, take 2. Compare 5 and 3, take 3. Compare 5 and 9, take 5. Compare 8 and 9, take 8. The left is exhausted, so drain the rest of the right. 9. Result: 1, 2, 3, 5, 8, 9. Each comparison emits one element, so merging to halves of total size n costs about n steps. Linear per level, and that's where the n in n-login comes from. Quicksort also divides, but cleverly in place. Pick a pivot, partition the array so smaller elements go left and larger go right, then recurs on each side. On average, it's n-login and very fast in practice with little extra memory. Its weakness, as we said, is a worst case of quadratic on bad pivots, and it isn't stable. Merge for guarantees, quick for raw speed. One partition, traced. The operation gate asks you to draw array 5, 2, 8, 1, 9, 3, and we choose the last element, 3, as the pivot. Walk left to right, collecting elements that are at most 3 to the front. 5, bigger, skip. 2, keep. It joins the small group. 8, skip. 1, keep. 9, skip. 2 elements were at most 3, so the pivot belongs at index 2. Swap it there. The array becomes 2, 1, 3, 5, 9, 8. Look at the result. Everything left of 3, 2 and 1 is smaller. Everything right. 5, 9, 8 is larger. The pivot is now in its paksh-faulted position, and we recurse on the two sides. That partition step is linear. Do it login times on good pivots, and you get n-login. A typical multiple choice. Which sort is both stable and guaranteed n-login in the worst case? Quicksort fails. Quadratic worst case and unstable. Heap sort fails. Unstable. The answer is merge sort, the only one ticking both boxes. These property tables, stable or not, in place or not, worst case, are pure recall marks. Build the table once, own it forever. To fundamental structures, defined by where you add and remove. A stack is last in first out, like a stack of plates you take from the top. That's how function calls and undo work. A queue is first in first out, a real queue, served in arrival order. That's how scheduling and, importantly, breadth first search work. A dequeue allows both ends. The discipline of access is the whole idea. Predict the outputs as the same operations hit each structure. On a buck stack Asto push 1, push 2, push 3. 3 is on top. Pop, out comes 3. Last in, first out. Push 4. Pop, out comes 4. So the popped sequence is 3, then 4, and 1 and 2 remain. Now the vict queue has any moves. NQ1, 2, 3. Dequeue. Out comes 1, first in, first out. NQ4 dequeue. Out comes 2. The dequeued sequence is 1, then 2, leaving 3 and 4. Same inputs, opposite outputs, because the only difference between these structures is bhaut which end as you remove from. Arrays versus linked lists is a trade-off in access versus insertion. An array stores elements side by side, so jumping to index 500 is instant. But inserting in the middle means shifting everything. A linked list chains nodes by pointers, so inserting where you already are is instant. But reaching the nth element means walking n links. Fast access or fast middle insertion. Pick your structure by what you do most. Here's a subtler idea the exam likes. Amortized cost. A global array starts small and sped doubles. Doubling means copying everything to a bigger block, which sounds expensive. Order n on that one insert. But how often does it happen? At sizes 1, 2, 4, 8. And the copy sum 2 1 plus 2 plus 4 plus 8, 15, to insert 16 items. Those costly resizes are rare and spread out. So when you average the total work over all the inserts, each push costs only a small constant, about 2 operations. That's amortized analysis. Not the worst single step, but the average over a whole sequence. A pricey operation that happens rarely enough is still cheap butter on average star. A hash table is how we get that near-instant lookup. A hash function turns a key into a bucket index. So you jump straight to where a value lives, constant time on average. The complication is a collision. When two keys hash to the same bucket. Linear probing resolves it by simply walking to the next open slot. Lookups stay fast, while the table isn't too full. Pack it tight, and performance degrades. Worked? With linear probing? Table of size 10. Insert 23, 13, 33. All hash to bucket 3. Since they all end in 3. 23 takes slot 3. 13 wants 3. It's taken. So it probes forward to slot 4. 33 wants 3, then 4. Both taken. Lands in slot 5. Trace the probes in order and the final table falls right out. A guaranteed exam pattern. A fuller probing trace. Table size 7, hash is keymod 7. 10 goes to slot 3. 22 goes to 1. 31 wants 3. Taken by 10, probe to 4. Open, place it. 4 wants 4. Now taken by 31. Probe to 5. Place it. 15 wants 1. Taken by 22. Probe to 2. Place it. 28 wants 0. Open. Place it. And 17 wants 3. Taken. 4 taken. 5 taken. 6 open after 3 probes. Place it. Read the final table left to right. 28, 22, 15, 10, 31, 4, 17. Notice the clusters forming. Each collision can push later keys further, which is exactly why a two-full table slows down. Same keys, but now resolving collisions by best chaining should. Every bucket holds a little linked list, and colliding keys just join the list. Bucket 0 holds 28. Bucket 1 holds 22 and 15. Bucket 3 holds 10, 31, and 17. A chain of 3. Bucket 4 holds 4. The contrast gate tests. With chaining, the table never fills up. Collisions only lengthen a list, and search cost is the length of that bucket's chain. With probing, collisions spill into other slots and form clusters, and the table can saturate entirely. Chaining trades a bit of pointer memory for graceful degradation. Probing stays cache-friendly but clusters. Know which one the question is describing. Trees branch. A binary search tree keeps an order. Everything smaller goes left, larger goes right. The magic consequence, an in-order traversal, left root right, reads the values out in sorted order. There's also pre-order, root first, and post-order, root last, each useful for different tasks like copying or deleting a tree. For a BST, remember, in order equals sorted. Let's build a tree and read all 3 traversals. Insert in this order. 50 becomes the root. 30 is smaller, goes left. 70 is larger, goes right. 20 is smaller than 50 and smaller than 30, left of 30. 40 sits between 30 and 50, right of 30. 60 is right of 50, left of 70. 80 is right of 70. Now traverse. In order, left, root, right. Gives 20, 30, 40, 50, 60, 70, 80. Sorted, as promised. Pre-order. Root first, then left subtree, then right. Gives 50, 30, 20, 40, 70, 60, 80. Post-order. Left, right, root last. Gives 20, 40, 30, 60, 80, 70, 50. The root, 50, comes prior to a level, and S to quintiles F all you use next. A different tree discipline now. a binary min heap, where every parent is smaller than its children, so the minimum always sits at the root. We store it as an array and insert by placing each new value at the end. Then fuck bubbling it up as, while it's smaller than its parent. Insert 15. Just 15. Insert 9 is smaller than 15, so it bubbles up to become the new root. 9 15. Insert 20. Bigger than 9, it stays at the end. 9 15 20. Insert 3. It's tiny. It bubbles up past 15, then past 9, all the way to the root. 3 9 20 15. Insert 12. It lands under 9 and 12 is bigger than 9, so it stays put. 3 9 20 15 12. Insert 7. It lands under 20, 7 is smaller, so it swaps up past 20, then stops, because 7 is bigger than the root 3. The heap array is now 3 9 7 15 12 20. Now extract the minimum. The whole point of a heap, the root, 3, comes out. To refill the root, move the last element, 20, up to the top. Then fuck. Sift it down fuck. Compare it to its children 9 and 7. Swap with the smaller, which is 7, and it settles there. The heap becomes 7 9 20 15 12, and we return 3. Both insert and extract touch only one root to leaf path, so each costs order log n. That's why a heap is the engine behind priority queues and heap sort. A favorite puzzle. Rebuild a tree from its traversals. Preorder's first element is always the root. Here, 5. Find 5 in the in-order list. Everything to its left, 1 3 4, is the left subtree. Everything right, 8, is the right. Recurs on each piece. Pre-order or post-order zest with the in-order pins down a unique tree, but 2 of them without in-order does not. That asymmetry is the trap. Try a bigger reconstruction. Pre-order 7 3 1 5 11 9 13. In-order 1 3 5 7 9 11 13. The first pre-order value, 7, is the root. Find 7 in the in-order list. To its left lie 1, 3, 5, the left subtree, and to its right, 9, 11, 13, the right subtree. Now recurs on the left. The next pre-order value is 3. So 3 is that subtree's root. In-order splits it into 1 on the left and 5 on the right. The right subtree's root is 11, splitting into 9 and 13. The tree is pinned down uniquely. As a check, read its post-order. 1, 5, 3, 9, 13, 11, 7. And the root 7 lands last, exactly where post-order puts it. Graphs are nodes joined by edges, networks, maps, dependencies. 2 ways to store one. An adjacency matrix is an n-by-n grid, a one where an edge exists. Instant edge lookups but n-squared space, wasteful when edges are few. An adjacency list keeps, per node, a list of its neighbors, compact for sparse graphs. Dense graph, lean toward the matrix. Sparse graph, the list. 2 ways to explore a graph. Breadth-first search uses a queue and fans out level by level. All neighbors first, then their neighbors. So it finds the fewest edges path. Depth-first search uses a stack, or recursion, and plunges as deep as possible before backtracking. Queue means breadth. Stack means depth. The structure you use literally determines the order you visit. Trace both on a tiny graph. A connects to B and C, and both reach D, starting at a breaking ties alphabetically. Breadth first visits A, then both neighbors B and C, then D, A, B, C, D. Depth first goes A into B, down to D, then back up to the unvisited C, A, B, D, C. Gate loves exactly this. Give the visit order, so always state your tiebreak rule and march the frontier carefully. A bigger graph to make the difference vivid. 7 nodes, edges A to B, A to C, B to D, BAE, CF, DG, EF, FG, ties broken alphabetically. Breadth first from a uses a Q. Visit A, Q its neighbors B and C. Take B, Q its new neighbors D and E. Take C, Q F. Then drain the Q in order D, then E, then F, and finally G. So breadth first is A, B, C, D, E, F, G. A tidy level by level sweep. Depth first from a plunges instead. A into B into BS first neighbor D, into DS neighbor G, into GS neighbor F, into FS neighbor C. CS only new option is none. Back up to FS neighbor E. So depth first is A, B, D, G, F, C, E. Same graph, same start, same tiebreak. And the orders diverge completely purely because a queue explodes wide and a stack explodes deep. Topological sort. Worked on prerequisites. Edges point from a course to the one it unlocks. A unlocks B and C. B and C both unlock D. D unlocks E, and B also unlocks E. Compute each nodes in degree. How many arrows points Pelican star? A has 0. B1, C1, D2, E2. The method. Repeatedly take a node with in degree 0. It has no unmet prerequisites, and remove it, decrementing its neighbors. Only A is free. So take A, that drops B, and C to 0. Alphabetical tiebreak takes B, then C. Now D drops to 0 and E drops to 1. Take D. E drops to 0. Take E. The order is A, B, C, D, E, and every edge points forward in that list, which is the definition of a valid schedule. This only works on a directed bi-acyclic acyclic graph. A cycle would leave nodes that never reach in degree 0. To more, you should recognize. Topological sort orders the nodes of a directed acyclic graph, so every edge points forward. Exactly how you'd schedule tasks with prerequisites. And for shortest paths with edge weights, Dijkstra's algorithm repeatedly settles the nearest unfinished node, relaxing its neighbors. You don't need to grind every step in this video, but let's do one, because seeing it once makes the idea stick. 1. Dijkstra fully. Source A edge weights labeled. Start. Distance to A is 0. All others infinity. Settle the nearest unfinished node, that's A, at 0, and relax its edges. B becomes 4 via the direct edge. C becomes 1. Now the nearest unsettled is C at 1. Settle C and relax. Through C, B could be 1 plus 2. That's 3. Better than the 4 we had. So update B to 3. And D becomes 1 plus 5, 6. Next nearest is B at 3. Settle B and relax. D through B is 3 plus 1, 4. Better than 6. Update D to 4. E through B is 3 plus 7, 10. Next is D at 4. Relax E to 4 plus 3, 7. Better than 10. Finally settle E at 7. The shortest distances from A are R0, C1, B3, D4, E7. Watch the lesson. The cheapest way to B wasn't the direct edge of 4. It was the detour through C for 3. Dijkstra always expands the nearest frontier node and asks that fuck greedy choice is what guarantees the answer. Your turn first, then we settle it together. A fresh graph, source S, weighted undirected edges. Distance to S is 0. Everything else infinity. Settle S, the nearest at 0, and relax its edges. A becomes 2, B becomes 6. The nearest unsettled is now A at 2. Settle A and relax. B through A is 2 plus 3, 5. Better than the 6 we had, so update B to 5, and C becomes 2 plus 5, 7. Next nearest is B at 5. Settle B and relax its one useful edge. D through B is 5 plus 1, 6. Next is D at 6. Settle D and relax. C through D would be 6 plus 2, 8, worse than the 7 C already has. So C stays 7, and T becomes 6 plus 7, 13. Next is C at 7. Settle C and relax. T through C is 7 plus 4, 11. Better than 13, so update T to 11. Finally settle T at 11. The shortest distances from S are S0, A2, B5, C7, D6, and T11. And notice the winning route to T threads, S, A, C, T for 11. Quietly beating the tempting, more direct-looking S, B, D, T, which costs 14. Greedy, one nearest node at a time, and the distances fall out in settled order. Programming and algorithms, locked. Read code by tracing values patiently. Watch for aliasing, mutable defaults, and that assigning a name inside a function makes it local. Big O is the shape of growth. Drop constants, keep the dominant term, and watch for halving, which means logarithms. The master theorem settles the rest in one comparison. Pick the data structure by the operation you do most. And searching a graph is breadth first with a queue, depth first with a stack, while Dijkstra greedily settles the nearest node for weighted shortest paths. Cost counting is now a reflex. We can compute and we can measure the cost. But most real data doesn't live in a variable. It lives in a database, queried by millions. Next, the relational model, SQL, and how we design tables that never lie. Databases and warehousing. A spreadsheet lets you store anything, including the same fact 3 times, 2 of them wrong. A database's real job is to store truth shack without contradiction and answer questions about it fast, for thousands of users at once. Gate tests 2 things here: writing and reading queries by hand, and designing tables that structurally can't hold a contradiction. Let's build both. The relational model is just tables, with precise names. A table is a relation. A row is a tuple. One fact. A column is an attribute, and the set of values it's allowed is its domain. The list of columns and their types is the schema, the table's blueprint. Rows have no inherent order, and ideally no 2 rows are identical. Plain tables, rigorously defined. Before tables, you sketch the design as an entity relationship diagram. Entities are the nouns, student, course, drawn as rectangles. Relationships connect them, enrolls with a cardinality, one-to-one, one-to-many, or many-to-many. The mapping rule worth knowing. A many-to-many relationship can't live in either table, so it becomes its own bridge table holding the 2 keys. Design in diagrams, then translate 2 tables. Count the tables this design needs. A favorite quick question. Top. Students and courses with a many-to-many enrolls, and each enrollment carries a grade. Each entity is a table, so that's 2. And because it's many-to-many, the relationship can't fold into either side. It becomes a third table holding the student key, the course key, and the grade. 3 tables. Bottom. A department employs many employees, one-to-many. Here the relationship PES can fold in. Just drop the department key as a foreign key into the employee table. No third table. 2. The rule. Many-to-many always costs a separate table. One-to-many tucks into the many side. Keys are how rows stay identifiable and linked. Any set of columns that uniquely identifies a row is a superkey. Trim it until nothing's wasted, and it's a candidate key, a minimal unique identifier. You crown one candidate as the primary key, and a foreign key is a column pointing to another table's primary key, enforcing referential integrity. You can't reference a student who doesn't exist. Keys are the database's promises of consistency. Relational algebra is the math behind queries, operators that take tables and return tables. Selection, sigma, keeps the rows matching a condition, the horizontal filter. Projection, pi, keeps only certain columns, the vertical slice, and it quietly removes duplicates. There's also union, difference, and intersection on compatible tables. These few operators, combined, express almost any query. Evaluate an expression on a tiny table. Work it inside out, like algebra. Table R with columns A and B, 1x, 2y, 3x, 4x. The expression is project A of select where B equals x. Innermost first, selection, where B equals x, keeps 3 rows, 1x, 3x, 4x. The y row is gone. Now project onto A1, 3, 4. 3 rows, always evaluate the inner operator first. And remember, projection drops duplicate values. Here all 3 values differ, so all 3 stay. The powerhouse is the join. It stitches two tables together by matching a shared column, so you can combine students with their enrollments. A natural join matches on common attributes automatically. And the trickiest operator, division, answers for all questions, which students took fit every required course. Selection and projection filter, joins combine, division handles for all. That vocabulary maps straight onto SQL. Count the rows a join produces. Predict first, then check. Table R on A and B has 2 rows with A equal to A and 1 with A equal to B. Table S on A and C has 2 rows with A equal to A and 1 with A equal to B. Natural join matches on A for the value A. Every matching R row pairs with every matching S row, 2 times 2, 4 rows. For B, 1 times 1, 1 row. Nothing else matches. Add them. 5 tuples. A natural join multiplies counts asterisk, it then find each matching key value. Then sums across values. Not a flat product of the table sizes. Work the hardest operator. Division, the for all, by hand. I took table pair students with courses. Amy took databases, AI, and machine learning. Bob took only databases. Kara took databases and AI. The required set is 2 courses, databases and AI. Took divided by that set returns every student who took PES, every F required course, not just some. Check each student against both requirements. Amy has databases and AI, plus an extra that does no harm. She qualifies. Bob has databases but is missing AI. He's out. Kara has exactly databases and AI. She qualifies. The result is Amy and Kara, 2 students. Division is the only operator that answers for all the required values, and you test it 1 candidate at a time, demanding the asterisk whole 1 required set. There's a second, declarative style, tuple relational calculus. Instead of specifying the steps like algebra, you describe the result. The set of all tuples T, such that some condition is true. It says, shuckin', what pya you want, not pya, how awful to get it. That declarative spirit is exactly what SQL inherits. You state the answer's shape and let the database figure out the procedure. SQL is that idea, productized. Select the columns from a table where rows meet a condition, group by some column to form buckets, having to filter those groups, order by 2 sort. The trap to internalize. It doesn't shock top to bottom. Conceptually, from and where run first, then group by, then having, then select, then order by. Knowing that order is how you predict results by hand. Compute 1 by hand. A sales table with regions and amounts. North 10, South 20, North 30, South 5. Group by region, sum the amounts. Where runs first? None here. Then group by gathers the 2 north rows and the 2 south rows into buckets, and sum collapses each. North is 40, South is 25. Form the buckets. Then aggregate within each. That's every group by question. Now a harder trace. Group by, then a having filter. 5 employees, Asha and Ravi in sales, Maya, Sam, and Ned in tech, earning 90, 60, and 90. The query. Select department and average salary. Group by department, having count of rows at least 3. Walk the execution order. Group by first, a sales bucket with 2 rows, a tech bucket with 3. Now having, it filters Beckett's 40 not rows. Sales has only 2 rows, fails the cut, and vanishes entirely. Tech has 3, survives. Finally, compute the average for the surviving bucket. 90 plus 60 plus 90 is 240. Over 3 equals 80. The output is a single row. Tech 80. The lesson, where filters rows before grouping, having filters whole groups after, and a group that fails having disappears completely, average and all. Now design, and it rests on functional dependencies. A determines B means any 2 rows that agree on A must agree on B. Knowing a student's ID determines their name. From a set of these dependencies, you can derive more, using 3 rules: reflexivity, augmentation, and transitivity. The single most useful computation built on them is the attribute closure, which decides keys and normal forms. Compute an attribute closure. This is a guaranteed exam skill. Relation A through E, with A gives B and C gives D, B gives E. Start with A pulls in B and C. Now C pulls in D. Now B pulls in E. Your set is A, B, C, D, E. Everything. Since A alone determines every attribute, A is a candidate key. Start with an attribute. Keep applying dependencies until nothing new appears. If you reach all attributes, you found a key. A trickier set, find fight-backing candidate keys, not just one. Relation A, B, C, D, with A to B gives C gives D, and D gives A. First, a shortcut that saves enormous time. Scan the right-hand sides. C, D, and A all appear on the right, but B never does. An attribute that nothing determines can't be reached by any closure. So B must first sit in every candidate key. Now try pairing B with each other attribute. A to B closure. A to B gives C gives D, D gives A. That's all 4. So A to B is a key. B to C closure. C gives D, D gives A, and we have B. All 4. So B to C is a key. B to D closure. D gives A, then A to B gives C. All 4 B to D is a key, and each is minimal, since B alone or any single attribute can't reach everything. So 3 candidate keys, A to B, B to C, and B to D. The trick that cracks these: an attribute appearing on no right-hand side is forced into every key. Redundancy is the enemy. Store a supplier's address in 50 rows, and one update can leave 50 contradictions. Normalization splits tables to kill that. First, normal form, atomic values, no repeating groups. Second, remove partial dependencies on part of a key. Third, remove transitive dependencies, where a non-key field determines another non-key field. Each form removes a specific class of anomaly. Climb the ladder, lose the redundancy. Let's see why ship splitting helps. The 3 anomalies, concretely. A supplier table holds supplier ID, name, city, plus a part and a quantity. And a supplier's ID determines its name and city. Because one supplier sells 3 parts, its city is copied across 3 rows. Now the trouble. Update, change that city in just 1 row, and the table now claims one supplier lives in 2 cities. A contradiction. Insert. You sign a new supplier who hasn't sold anything yet, but every row needs a part, so you can't even record them. Delete. Remove a supplier's last part, and you accidentally erase the supplier's name and city too. All 3 come from one root cause, a fact about the supplier stored over and over. Split into a supplier table holding ID, name, city, and a supplies table holding ID, part, quantity. Now each supplier's city lives in exactly one place. Update touches 1 row. You can add a supplier with no parts, and deleting a part can't lose the supplier. Normalization isn't tidiness. It's storing each fact exactly once, so it can never disagree with itself. The cleanest rule to memorize is Boycott normal form. For 1K, every S functional dependency, the left side must be a superkey. If anything that isn't a superkey determines another attribute, you're not in BCNF. Split it out. Third, Normal form is a touch more permissive, allowing a dependency if the right side is itself part of a key. BCNF is the strong target. Know the superkey test. Classify 1. Relation A, B, C. A determines B and B determines C. A is the key. Is it in third normal form? No. B determines C. But B isn't a superkey, and C isn't part of a key. So that's a transitive dependency. A to B to C. With a single attribute key, there are no partial dependencies. So it clears second normal form but fails third. Highest normal form, 2NF. Split into A to B and B to C, and both pieces are clean. A subtler classification, find the highest normal form and the FD that blocks the next one. Relation A, B, C, with A to B gives C and C gives B. First, the candidate keys. A to B closure reaches all three, and A to C closure. C gives B, so A, C, B also reaches all three. To candidate keys, A to B and A to C. Notice that A, B, and C are astroc prime. Each sits in some candidate key. Now test BCNF, the superkey rule, on each dependency. A to B gives C. A to B is a key. Fine. C gives B. Is C a superkey? CS closure is just C and B. Not everything, so no. That breaks BCNF. But check 3NF's gentler rule. 3NF forgives a dependency when its right side is a prime attribute, and BFARC is S-Groim attribute. So C gives B is allowed in third normal form. The highest normal form is 3NF, and the dependency that stops it reaching BCNF is C gives B. This exact shape, a prime attribute on the right, is the gap between 3NF and BCNF. When you split a table, two properties matter, and the trap is treating them as the same. A decomposition is lossless if joining the pieces back gives you exactly the original with no spurious rows. That one is mandatory. Losing data is never acceptable. The second, dependency preservation, means every original dependency can still be enforced on a single piece without rejoining. BCNF always gives you lossless, but can sometimes cost you dependency preservation, and that trade-off is the exam question. Test a split for losslessness. There's a one-line rule. Relation A, B, C with a gives B and B gives C. Split it into an A to B table and A B to C table. The rule. A two-way decomposition is lossless exactly when the column they share is a key of at least one piece. The shared column here is B. Is B a key of either piece? B's closure is B and C. So B determines all of the B to C table. Yes, B is a key there, lossless. Now the contrast, in red. If instead you'd split into an A to C table and A B to C table, the shared column is C, whose closure is only C, a key of neither piece. That join would manufacture phantom rows, lossy. So, find the common attribute, take its closure, and check whether it's a key of one of the two tables. Now test the same split for dependency preservation. The original dependencies are a gives B and B gives C. Look at where each one can be checked. A gives B lives entirely inside the A to B table. Both columns are there, so that table enforces it. B gives C lives entirely inside the B to C table. Every original dependency is enforceable on a single piece. No join needed. So the decomposition preserves dependencies. And we already showed it's lossless. This split wins on both counts. But that happy ending isn't guaranteed. Sometimes chasing the strongest normal form forces you to give one up. Here's the deep one. Why BCNF can cost you a dependency with the textbook example. Take the relation we just classified, A, B, C, with A to B gives C and C gives B. We found its candidate keys are A to B and A to C, and it sits in 3NF but not BCNF. Because C gives B and C isn't a super key. To force it into BCNF, you must split on that offending dependency. Pull out a B to C table and leave an A to C table. The B to C table happily enforces C gives B. But look at the other original dependency. A to B gives C. Its left side, A to B, is split across the two tables. A is in one piece, B in the other. There is one no-fit single table where you can check it. You'd have to join them back first. So this BCNF decomposition is not dependency preserving, and that's the unavoidable trade-off Kate loves to probe. The 3NF version kept every dependency checkable but tolerated a little redundancy from C gives B. Pushing all the way to BCNF removed that redundancy but lost the ability to enforce A to B gives C locally. Lossless is always achievable. Dependency preservation up to BCNF is sometimes simply impossible. To query fast, you index. A B plus tree index keeps keys sorted in a shallow, bushy tree, so both exact lookups and funner when aged 30 to 40. A hash index is even faster for exact matches but useless for ranges. And a clustered index actually orders the rows on disk, so there can be only one. Choose the index by the query. Ranges want a tree. Exact hits can use a hash. Choose the right index for each query. Predict before the reveal. Query 1 asks for every salary between 30,000 and 50,000. A asterisk range star. A B plus tree keeps keys in sorted order, so a range is one continuous sweep along the leaves. Pick the tree. A hash index would scatter those nearby salaries to random buckets, making a range scan useless. Query 2 asks for the employee whose ID equals exactly 4217, a single fight equality ASWEM match. A hash index jumps straight to the bucket in essentially constant time. It's ideal. A B plus tree would also answer it, just with a logarithmic walk down the tree. The rule that decides every such question. Ranges and sorting want a B plus tree. Pure equality lookups can use a hash. Warehousing also means shits transforming chit data for analysis, and these double as machine learning pre-processing. Normalization rescales features to a common range, so one big numbered column doesn't dominate. Discretization bins a continuous value into categories. Sampling takes a manageable subset. Compression shrinks storage. Remember this list. When we hit machine learning, scale your features will mean exactly this normalization step. Apply min-max normalization to one number, a tiny but examinable computation. An age column runs from a minimum of 20 to a maximum of 60, and you want to rescale it to the 0 to 1 range. The formula is the value minus the minimum over the maximum minus the minimum. For an age of 35, 35 minus 20 is 15. 60 minus 20 is 40. 15 over 40 is 0.375. The minimum maps to 0, the maximum to 1, and everything else lands proportionally between. That single rescaling is exactly what feature scaling will mean in machine learning. For analytics at scale, we model differently, around a central fact. A star schema puts a big fact table in the middle. Each row a measured event like a sale, surrounded by dimension tables describing the context, date, store, product. It's denormalized on purpose for fast reads. A snowflake schema normalizes those dimensions further into subtables. Tidier, but more joins. Star for speed, snowflake for cleanliness. On top sits OLAP, analysis over a data cube. A concept hierarchy lets you move between levels. Day rolls up to month, rolls up to year. Rollup aggregates to a coarser view. Drill down goes finer, and slicing fixes one dimension to inspect a cross-section. The numbers you aggregate, sales counts, totals, are the measures. This is the language of dashboards, and it's where databases hand off to data science. One quick OLAP computation, a rollup. Sales sit at the city level. Delhi 100, Mumbai 150, both in the north. Chennai 80, Bangalore 120, both in the south. Rollup climbs the concept hierarchy from city to region and aggregates the measure. North becomes 100 plus 150, 250. South becomes 80 plus 120, 200. Roll-up always best aggregates upward folk to a coarser level. Drill down is the exact reverse, expanding region back into its cities. Same numbers, viewed at the level you ask for. Your turn, pause and solve before the reveal. Relation A, B, C, D, with a gives B, a gives C, and B to C together give D. Compute the closure of A, and decide whether A is a candidate key. Pause it now. Start with A gives B, so add B. A gives C, so add C. Now you hold both B and C. And B to C gives D, so add D. Your closure is A, B, C, D. Every attribute alone determines the whole relation. So yes, A is a candidate key. If you chain the dependencies until nothing new appeared and landed on all four, you've mastered the one skill this chapter is built on. Databases. Locked in. The relational model is tables with keys that enforce consistency. Relational algebra and SQL query them, and you can now trace a join, a group by, and a having by hand. Attribute closure finds every candidate key and drives normalization up to BCNF, where every determinant is a superkey, though sometimes at the cost of dependency preservation. And for analytics, the star schema centers on facts surrounded by dimensions. We've stored the data and cleaned it. Now we make it predict star. This is the heart of the paper. The biggest single block of marks. Machine learning. Everything we've built, probability, linear algebra, calculus, comes together here. Let's go. This is where it all comes together. Probability handles the uncertainty. Linear algebra moves the data. Calculus does the optimizing. And machine learning fuses them into something that predicts. The core idea is a turn of the wrist. Instead of writing rules by hand, we show machine examples and let it find the rules itself. It's the biggest block of marks in the exam. So settle in. Two big families. Supervised learning has labeled examples, emails marked spam or not, and learns to predict the label on new data. That splits into regression for numbers and classification for categories. Unsupervised learning has no labels at all, and instead finds hidden structure, like grouping similar customers, and one discipline rules both. Split your data, train on one part, and test on data the model has never seen, because anyone can memorize the past. That test set guards against the central villain, overfitting. A model that's too simple underfits, missing the real pattern. A model that's too flexible overfits, memorizing the noise and the exact training points, then failing on anything new. We want the middle, and the subtlest sin is data leakage. Letting any whisper of the test data into training, which flatters your score and betrays you in the real world. Test data is sacred. Never peak. The simplest model. Fit a straight line. Simple linear regression draws the line that best predicts y from x. Best means minimizing the squared vertical distances from points to the line, the residuals, and here's a thread from linear algebra. Finding that best line is exactly projecting the data onto the space the model can represent. The projection we met 2 parts ago. Least squares S is after a projection. We measure a fit by its cost, the mean squared error, the average squared residual. Plot that cost against the lines slope and intercept, and you get a smooth ball. A convex surface, exactly the friendly shape calculus promised, with a single lowest point. So fitting a line is an optimization. Find the slope and intercept at the bottom of the ball. For this one, we can even solve it in closed form. But the general tool is coming. Let's use a fitted line. Suppose least squares gave us y hat equals 2x plus 1. Predict the value at x equals 3. 2 times 3 plus 1, 7. Now, if the puck's actual data point there was 8, the residual, the model's error on that point, is 8 minus 7, 1. Square those residuals across all points. Average them. And that's the mean squared error the line was chosen to minimize. Prediction is plugging in. The residual is what's left over. Real problems have many features. Age, income, history, not one. Multiple linear regression fits a weighted sum of all of them. Each feature gets a weight saying how much it matters, plus an intercept. Geometrically, the line becomes a flat hyperplane through high-dimensional space. The math barely changes. The weights are just a vector now, and the sign and size of each weight is how the model tells you which features drive the prediction. How do we actually reach the bottom when there's no formula? We roll downhill. Gradient descent computes the slope of the cost, the gradient, and steps in the opposite direction, the steepest way down, over and over. The learning rate sets the step size, and it's everything. Too small, and it crawls for ages. Too big, and it leaps past the minimum and can diverge. This single algorithm trains almost every model in modern AI. One concrete step, say the cost is w squared, a simple parabola with its minimum at 0. Its gradient is 2w. Start at w equals 3, learning rate 1/10. The update is the current value minus the rate times the gradient. 3 minus 0.1 times 6, which is 3 minus 0.6, landing at 2.4. One step, and we've moved from 3 towards 0. Take another step to feel the convergence. From 2.4, the gradient is 2 times that 4.8. Subtract 0.1 of it, and you land at 1.92. Again, and you'd reach 1.54. Notice the steps automatically get smaller as the slope flattens near the bottom. Gradient descent naturally slows down as it closes in. 3, 2.4, 1.92. Marching steadily toward the minimum at 0. That's the engine. Iteration by iteration. Your turn, a parabola shifted, so its minimum sits at w equals 2. The cost is w minus 2, all squared. So the gradient is 2 times w minus 2. Start at 5 with a learning rate of 1/4. Step 1. The gradient is 2 times 5 minus 2, which is 6. Subtract 1/4 of 6, that's 1.5, landing at 3.5. Step 2. The gradient is 2 times 3.5 minus 2, 3. 1/4 of that is 0.75, so we reach 2.75. Step 3. The gradient is 2 times 0.75, 1.5. 1/4 is 0.375, landing at 2.375. 5, 3.5, 2.75, 2.375, and watch the gradients halve each time. 6, 3, 1.5, because with this rate, every step cuts the distance to 2 in half. Closing in on the minimum, never overshooting. To fight overfitting directly, we regularize. Ridge regression adds a penalty to the cost for large weights. Lambda times the sum of squared weights. Now the model is torn between fitting the data and keeping its weights small, so it can't contort into a wild overfit. This nudges bias up a little, but cuts variance a lot. Usually a winning trade. The strength, lambda, is a knob you tune, which is the perfect cue for the idea everything in this section orbits. It helps to see the extremes. With lambda at 0, the penalty vanishes and Ridge is just ordinary least squares, free to overfit. Crank lambda toward infinity and the penalty dominates, so every weight gets crushed toward 0 and the model underfits into a nearly flat line. The useful value lives in between, found by cross-validation. One aside worth knowing. Ridge uses squared weights and shrinks them smoothly, while its cousin Lasso uses absolute weights and can push some exactly to 0, doing feature selection for free. The bias-variance trade-off is the deepest idea in machine learning. So let's make it physical. Picture throwing darts. Bias is being consistently off-target. Your darts cluster tightly but in the wrong place. That's an underfit model, too simple to be right. Variance is being wildly inconsistent. Darts scattered all around the bullseye. That's an overfit model, swinging with every sample. You want tight fuck-centered. Almost no model is both naturally. Now watch the curves as we crank up complexity. Training error just keeps falling. A complex enough model memorizes everything. But test error traces AU. It falls as the model gets useful, then rises as it starts overfitting. Total error is roughly bias squared plus variance plus irreducible noise. And as one drops, the other climbs. The widening gap between training and test error roughly tracks the variance. The art is parking at the bottom of that U, the sweet spot between too simple and too complex. This single picture explains regularization, model size, and most tuning you'll ever do. Diagnose two models from their errors alone. Model A scores 3% error on training and 4 on test, both low and close together. That's a healthy fit. Model B scores 0 on training but 18 on test. Perfect on what it has seen, terrible on what it hasn't. That enormous gap is the unmistakable signature of high variance, of overfitting. The fix isn't more power, it's less. Regularize it, simplify it, or feed it more data. Reading these two numbers is half of practical machine learning. But how do we find Pandad's that sweet spot honestly, without touching the sacred test set? Cross-validation. Split the training data into, say, 5 folds. Train on 4, validate on the 5th, then rotate so each fold takes a turn as the validator, and average the 5 scores. You get a stable estimate of real-world performance from limited data. Livennout takes it to the extreme. One example per fold. Stratified keeps class proportions intact. This is how you tune lambda and pick models. For classification, accuracy alone lies. So we lay out the confusion matrix. 4 boxes. True positives, correctly caught. True negatives, correctly cleared. False positives, false alarms, and false negatives, the misses. Every classification metric is just a ratio of these 4 numbers. Get comfortable placing predictions into these 4 boxes, because the exam questions are built straight on top of them. 2 metrics matter most, and they pull against each other. Precision asks, of everything I flagged, how much was right? Recall asks, of everything I should have caught, how much did I find? Tighten your net for precision and you miss cases, hurting recall. Cast wide for recall, and you collect false alarms, hurting precision. The threshold you choose slides you along that seesaw. Compute them. 40 true positives, 10 false positives, 20 false negatives, 30 true negatives. Precision is 40 over the 50 we flagged, 0.8. Recall is 40 over the 60 that were actually positive, about 0.67. Accuracy is the 70 correct over 100.7. Notice precision and recall disagree, telling a richer story than the single accuracy number. Place the 4 counts. Then it's just division. When you want one number that respects both, use F1, the harmonic mean of precision and recall, 2PR over P plus R. With precision 0.8 and recall 0.67, that's 2 times 0.8 times 0.67. Over their sum, about 0.73. The harmonic mean deliberately sits closer to the asterisk smaller or 2. So you can't fake a good F1 by acing one metric and tanking the other. Both have to be decent. Now the trap, with numbers that bite. 1,000 patients, only 10 actually sick. A lazy model predicts healthy for everyone. Its accuracy? 990 right out of 1,000, 99%. Sounds brilliant. But its recall on the sick is 0 out of 10. It caught nobody. A 99% accurate model that is completely worthless. This is why, on imbalanced problems, you report precision and recall. Never accuracy alone. The single most important habit in applied ML. Run the full battery on a fresh table. 200 cases. 30 true positives. 20 false positives. 10 false negatives. 140 true negatives. Precision is 30 over the 50 we flagged, 0.6. Recall is 30 over the 40 truly positive, 0.75. F1 the harmonic mean is 2 times 0.6 times 0.75, which is 0.9. Over there some 1.35, about 0.67. sitting nearer the smaller of the two as it should. And accuracy is the 170 correct over 200.85. Now the trap. A lazy model that predicts negative for everyone scores 160 over 280% accuracy. Yet its recall is 0 out of 40, catching not a single positive. 80% accuracy, utterly useless. Always read precision and recall beside accuracy, never instead. A classifier doesn't have to commit to one threshold. The ROC curve sweeps the threshold from strict to lax and plots the true positive rate against the false positive rate. A model hugging the top left corner is excellent. The diagonal line is coin flip random. The area under that curve, the EUC, summarizes performance across all thresholds in a single number. 1, perfect. 1/2, worthless. It's how we compare classifiers independent of where we set the cutoff. Despite its name, logistic regression classifies. It takes the same weighted sum as linear regression, but pushes it through the S-shaped sigmoid, squashing any number into a probability between 0 and 1. Above 1/2, predict the positive class. Below, the negative, and that cutoff draws a linear decision boundary. So it's a linear model that outputs probabilities. And it's the workhorse baseline for yes or no problems. Put a number through the sigmoid. The sigmoid of 0 is 1 over 1 plus 1, exactly 1/2, which is why 0 is the decision boundary. Now suppose the model's weighted sum for some example comes out to 2. The sigmoid of 2 is 1 over 1 plus e to the minus 2, about 0.88. So the model is 88% confident it's positive, well above the halfway line. So we predict the positive class. The weighted sum sets the position. The sigmoid turns it into a probability. The laziest classifier, and a good one. K-nearest neighbors does no training at all. To classify a new point, it finds the K closest labeled points and takes a majority vote. Small k makes a jagged, twitchy boundary, high variance. Large K smooths it out, higher bias. There's the trade-off again. And the trap. It relies on distance. So if one feature ranges in thousands and another in fractions, the big one silently dominates. Always scale your features first. Remember normalization from databases. Classify the point 33 with k equals 3. Compute Euclidean distances. To B it's 1, to A about 2.2, to C about 2.8, to D farther. The three nearest are B, A, and C, 2 positives and 1 negative. Majority wins. Predict positive. List distances, take the case smallest. Vote. That's the entire algorithm. And a guaranteed worked question. The choice of k-JAS is variance dial. With k equals 1, the prediction is whatever single nearest point says. So the boundary contorts around every example, including the noise. Classic overfitting. Push k all the way to the dataset size, and every query just returns the overall majority class. Total underfitting. The truth sits between usually an odd number, so the vote can't tie. So even k-nearest neighbors, the simplest model here, lives and dies by bias versus variance. Naive Bayes brings probability back. It uses Bayes' theorem to ask, given these features, which class is most probable? The clever, lazy shortcut. The naive part is assuming the features are independent given the class, so their probabilities simply multiply. That assumption is usually false, yet it works astonishingly well, especially for text and spam. It's our rare disease-based reasoning, scaled up to many clues at once. A quick spam example. Spam and ham equally likely beforehand, 1/2 each. The word free appears in 80% of spam, but only 10% of ham. An email contains free. Score each class, spam, 0.8 times 0.5 is 0.4. Ham, 0.1 times 0.5 is 0.05. Normalize 0.4 over their sum, 0.45, and you get about 89% spam. Multiply the prior by the likelihoods, then normalize. Watch the naive multiplication with 2 clues. Add a second word, money, in 60% of spam and 30% of ham. An email has both free and money. Because we assume the words are conditionally independent given the class. We just multiply. Spam scores zero point 0.5 times 0.8 times 0.6, 0.24. Ham scores 0.5 times 0.1 times 0.3, 0.015. Normalize and it's about 94% spam. Each extra incriminating word multiplies in, and the evidence stacks fast. That multiply the likelihoods move is the whole algorithm. Linear discriminant analysis classifies by finding the best direction to Mutt's project chut, the one that pushes the class means far apart while keeping each class tight. Squash the data onto that line and the classes separate cleanly, giving a linear boundary. It's a cousin of PCA. But where PCA only cares about spreading the data out, LDA uses the labels to maximize class separation. Supervised projection, essentially. Support vector machines ask a sharp question. Of all the lines that separate two classes, which is best? The one with the widest margin, the biggest buffer zone between the classes, because that generalizes best. Only the points right on the edge of that margin matter. They're called the support vectors, and they alone define the boundary. Throw the rest away, and the model is unchanged. Maximum margin is the whole philosophy. But what if no straight line can separate the classes? The kernel trick. We imagine lifting the data into a higher dimension where it becomes separable by a flat plane. And the genius is, we never actually compute those high-dimensional coordinates because the math only needs dot products. A kernel computes them directly. Our linear algebra dot product, doing the heavy lifting. Curved boundaries in your world, straight ones in the hidden space. Decision trees classify by asking a sequence of yes or no questions, splitting the data at each step. But which question first? The one that best purifies the groups. We measure messiness with entropy, high when classes are mixed, 0 when a group is pure, or with the similar Gini index. The tree greedily picks the split with the largest information gain, the biggest drop in entropy. Ask the most separating question first. Compute an entropy, the classic gate warm-up. A node has 9 positives and 5 negatives, 14 total. Entropy is minus the proportion of each class times its log base 2. 9 14ths is about 0.64, whose log base 2 contributes 0.41. 5 14ths contributes 0.53. Add them. About 0.94 bits, close to a 50-50 mix. So entropy is high, near 1, the node is messy, and a good split should slash that number. Now a perfect split. A node with 4 positives and 4 negatives is maximally mixed, entropy exactly 1 bit, and Gini exactly 1/2. A feature splits them cleanly. All 4 positives one side, all 4 negatives the other. Each branch is pure. Entropy 0, Gini 0. So the information gain is the full 1 bit, and the Gini drops by the full half. A feature that perfectly separates the classes has information gain equal to the parent's entropy, and that's the feature the tree grabs first. Now an honest, imperfect split. The realistic case. A parent node has 6 positives and 6 negatives. A dead-even mix, so its entropy is exactly 1 bit. A feature splits it. The left branch gets 5 positives and 1 negative. The right branch 1 positive and 5 negatives. Each branch is purer, but not pure. Left entropy is minus 5/6 times its log base 2, about 0.22, minus 1/6 times its log, about 0.43, together roughly 0.65 bits. The right branch is the mirror image, also 0.65. Each branch holds half the data, so the weighted child entropy is just 0.65. Information gain is the parent minus that, 1 minus 0.65, about 0.35 bits. Positive, so the split helps. But it's no perfect one-beat gain. The tree compares this against every other feature and grabs whichever scores highest. Now toward neural networks, starting with one neuron, the perceptron. It takes inputs, weights them, sums, and fires a 1 or 0 through a threshold. It learns by a beautifully simple rule. On a mistake, nudge the weights toward the right answer. But one perceptron can only draw a straight boundary, so it famously can't solve XOR, a problem that isn't linearly separable. That limitation is exactly why we stack neurons into layers. Fire a perceptron by hand. Inputs 1 and 0, weights 0.5 and 0.5, bias minus 0.2. The net input is the weighted sum plus the bias, 0.5 times 1 plus 0.5 times 0 minus 0.2. That's 0.3. Positive. So the neuron fires a 1, feed it 0, 0 instead, and the net is just minus 0.2. Negative. So it outputs 0. A perceptron is literally weighted sum, add bias, check the sign. Everything deep is built from this one operation. Stack neurons into layers and you get a multi-layer perceptron. The hidden layers, each followed by a nonlinear activation like ReLU or sigmoid, are what give it power. Without that nonlinearity, stacked layers would just collapse back into one linear model. With it, a network with enough hidden units can approximate essentially any function, carving curved, intricate decision boundaries. Depth plus nonlinearity is the recipe for modern deep learning. A favorite exam question: count a network's parameters. 3 inputs feed a hidden layer of 4, which feeds 1 output. Every connection is a weight. 3 inputs times 4 hidden is 12, plus 4 hidden times 1 output is 4. 16 weights. Then each non-input neuron has a bias. 4 in the hidden layer plus 1 at the output. 5 biases. Total 21 learnable numbers. Weights count the arrows. Biases count the neurons they feed. That's the whole counting rule. How does a deep network learn its weights? Backpropagation, which is just the chain rule from calculus, applied cleverly. Compute the error at the output, then flow it asterisk backwards. Asterisk, layer by layer, using the chain rule to find how much each weight contributed to the mistake. Those are the gradients. And gradient descent nudges every weight to reduce the error. Forward to predict, backward to assign blame, then step downhill. That loop is how every neural network trains. Now unsupervised. No labels, just structure. K-means clustering groups data into K clusters through a simple loop. Drop K center points. Assign every data point to its nearest center. Then move each center to the average of its assigned points. Repeat, and the centers slide into the natural clusters and stop. K-medoids is the robust cousin that uses actual data points as centers, resisting outliers. Assign, update, repeat. That's the rhythm. One iteration on a line. Points 1, 2, 10, 11, with starting centers at 2 and 11. Assign each to the nearer center. 1 and 2 go to the first, 10 and 11 to the second. Now move each center to its cluster's mean. The first becomes 1.5, the second 10.5. Reassign. Nothing changes, so it's converged. The algorithm found the obvious 2 clusters in a single pass. Assign by distance, update by mean. Hierarchical clustering needs no K upfront. It starts with every point alone and repeatedly merges the 2 closest clusters, building a tree called a dendrogram. How you measure closest is the linkage. Single linkage uses the nearest pair of points. Complete uses the farthest. Average splits the difference. Slice the dendrogram at any height to get however many clusters you want. You see the whole structure, then choose. A tiny linkage trace. 3 points at 1, 2, and 5. The pairwise distances are 1 to 2 is 1, 2 to 5 is 3, 1 to 5 is 4. Agglomerative clustering merges the closest pair first. That's 1 and 2 at height 1. Then the remaining point, 5, joins that cluster at the next height. Reading the dendrogram from the bottom, the first merge is always the globally closest pair. Single linkage uses the nearest members to decide. That's the rule being applied. And the finale. Principal component analysis, the great compressor. Picture an elongated cloud of data tilted in space. PCA finds the single direction along which the data varies the most, the long axis of the cloud, and calls it the first principal component. The next component is perpendicular, capturing the most remaining variance. It's rotating your axis to align with the data itself. Where does the data truly live? PCA answers that. And here's the gorgeous payoff that ties this whole course together. Those principal directions are exactly the R-stroke of the data's covariance matrix, and each eigenvalue is the amount of variance along its direction. The same eigenvectors and singular values from linear algebra, now revealing the shape of data. Keep the top few components, project onto them, and you slash dimensions while keeping nearly all the information. Eigenvalues, covariance, projection, all of it in one technique. Put a number on it. Suppose the covariance matrix has eigenvalues 4 and 1. The first principal component explains 4 out of the total 5 units of variance, 80%. So you could drop from 2 dimensions to 1, keeping that single component, and still retain 80% of the information. That ratio, an eigenvalue over the sum of eigenvalues, is the variance explained. And it's exactly how you decide how many components to keep. One more, the way it's usually asked. 3 eigenvalues, 5, 3, 2, summing to 10. The first component carries 5/10, 50%. Add the second's 3/10, and you're at 80% cumulatively. So to retain 80% of the variance, you keep 2 components and discard the third, dropping from 3 dimensions to 2. That cumulative variance plot, the scree plot, and a target like 90 or 95% is exactly how dimensionality is chosen in practice. One you can predict. The covariance matrix has 4 eigenvalues, 6, 3, 2, and 1, summing to 12. The first principal component carries 6/12, exactly 50%. Add the second's 3/12, and you're at 9/12, 75%. Add the third's 2/12, and you reach 11/12, about 91.7%. Now the usual question. How many components to keep at least 90% of the variance? To only get you to 75, short of the target. So you need 3 components, which clear 90%, taking you from 4 dimensions down to 3, discarding only the smallest eigenvalue. Cumulative sum until you cross your threshold. Then count the components. That's the whole rule. One practical trap that's caught many. PCA chases variance. So if one feature is measured in thousands and another in fractions, the big numbered one will dominate the first component purely because of its units, not its importance. So before PCA, you center the data by subtracting the mean, and usually standardize every feature to the same scale. It's the same lesson as k-nearest neighbors. When geometry decides, scale your features first. Unscaled PCA quietly measures the wrong thing. That's machine learning, the largest territory on the map. Split your data and fear leakage. Fit models by rolling down a cost ball with gradient descent, and regularize to tame variance. Live at the bottom of the bias, variance U, found honestly with cross-validation. Judge classifiers with precision and recall, not accuracy. And from KNN to SVMs to neural nets to PCA, every one leans on the probability, algebra, and calculus you already own. Machine learning lets a system learn from data. But intelligence is also about pick reasoning S, searching for a plan, deducing with logic, inferring under uncertainty. That older, sharper side of AI is next. Search, logic, and Bayesian inference. Machine learning was about learning from data. But intelligence is also about fuck reasoning shit. Working out a plan, deducing a fact, inferring a cause. This is the classical side of AI, and it comes in 3 shapes: the exam tests. Searching through possibilities for a solution, using logic to deduce truths, and using probability to reason under uncertainty. Sharp, beautiful, and very scoreable. Most AI problems become search. You have a starting state, a set of actions that move you between states, and a goal you're trying to reach. Solving a puzzle, routing a map, planning moves. The possibilities form a giant tree, and the algorithm explores it, keeping a frontier of states waiting to be expanded. The whole game is which state to expand next, and that single choice defines every search algorithm we'll meet. Before the algorithms, 4 questions we'll judge every one of them by. Is it complete? Does it always find a solution if one exists? Is it optimal? Does it find the asterisk cheapest ping solution, not just any? How much time does it take, and how much memory? 2 letters set the scale. B. How many actions branch from each state? And D. How deep the goal lies. Keep these 4 yardsticks in mind, because the exam loves to ask exactly which property a method does or doesn't have. Uninformed search knows nothing beyond the goal test. Breadth first explores level by level using a queue. It's guaranteed to find a solution, and the shallowest one. But notice the fine print. Breadth first finds the asterisk optimal Astor solution only when every step costs the same. When the shallowest goal is also the cheapest. It also hoards memory, holding an entire level at once. Depth first plunges down one path using a stack, memory light. But it can wander down the wrong branch forever and isn't optimal. We met these exact traversals in the algorithm section. Here they're solving problems. 2 refinements. When edges have different costs, uniform cost search expands the node with the lowest cumulative cost so far, using a priority queue. That makes it optimal for weighted graphs, as long as every edge cost is non-negative, which is the condition that lets the cheapest so far node be safely locked in. It's the cost-aware version of breadth first, and iterative deepening combines the best of both. Run depth first to depth 1, then 2, then 3. Getting breadth first guarantees with depth first tiny memory footprint. A clever way to have it both ways. Let's run all 3 on one graph and watch them disagree. From S, 2 edges. To a costing 1 to be costing 5. Then A to C costs 1, C to G costs 1, and B straight to G costs 1. Pause and predict each algorithm's expansion order. Breadth first ignores costs and goes by level. It expands S, then A and B, then C, then G. And the first goal it reaches is along S to be 2G, 2 edges, but costing 6. Depth first dives down the first branch. S, A, C, G, finding S, 2A, 2C, 2G. Uniform cost goes by cheapest cumulative cost. It expands S, then A at 1, then C at 2, then G at 3. Order S, A, C, G, and returns S2A to C2G. Total cost 3. So breadth first found the fewest edges but not the cheapest path. Uniform cost found the genuinely cheapest. That gap is the whole point of waiting. And there's the trap, the last problem setup. People reach for breadth first and assume the shallowest goal is the best goal. It is, but only on a unit cost graph. The moment edges carry different weights, fewest edges and cheapest cost pathways, and you must switch to uniform cost or S star. If a question gives you numbers on the edges, that's your signal. Cost matters, and breadth first optimality guarantee has quietly evaporated. One worry about iterative deepening deserves a worked answer. Doesn't rerunning depth first from scratch each round waste effort? Picture the passes. Depth limit 0 touches the root. Limit 1 retouches the root and its children. Limit 2 retouches all of that plus the next level. The top levels pass are asterisk re-expanded every pass. But here's the saving grace. In a tree that branches by B, each level holds B times as many nodes as the one above. So the deepest level alone outweighs everything above it combined. The repeated work is a small constant overhead, and the total stays on the order of B to the D. The same as breadth first, but with depth first's tiny memory. That's why iterative deepening is the textbook default when the tree is deep and memory is tight. Now we add intelligence, a heuristic, an educated guess of how far a state is from the goal, like straight line distance on a map. Two properties decide whether it's safe. A heuristic is admissible if it never estimates the true remaining cost, always optimistic. It's consistent, a stronger condition, if its estimate drops by at most the edge cost as you take a step. Admissibility is the magic ingredient for the next algorithm's optimality. Test a heuristic the way gate does. Here the put true remaining cost from A is 3, from B is 5, from C is 1. The candidate guesses 2, 4, and 2. Admissible means never above the truth. 2 is at most 3, 4 is at most 5. But at C, the guess 2 is as to put above vert, the true remaining cost of 1. One overestimate is enough. This heuristic is not admissible. Now consistency, the triangle check. Along every edge, the heuristic must drop by no more than that edge's cost. Take an edge from B to C costing 1. The guess falls from 4 to 2, a drop of 2. But the edge only allows a drop of 1. So consistency fails there too. One bad cell sinks the whole property. Check every node, not just the start. And the most important search algorithm A star. It evaluates each node by F equals G plus H. G, the real cost to get here, plus H, the estimated cost to go. Greedy search uses only H and rushes recklessly toward the goal. Uniform cost uses only G and ignores the goal entirely. A star fuses them, balancing where you've been against where you're headed. With an admissible heuristic, it's guaranteed to find the optimal path. And that guarantee is why it's everywhere. Pause on pick. Why should impossibility forces optimality? The intuition is lovely. Suppose the true cheapest cost to the goal is some number. Call it C star. Take any node sitting on that optimal path. Its F is the real cost to reach it plus an honest, never too high guess of the rest. So its F can never exceed C star. Meanwhile, any worse goal that's still on the frontier has an F strictly above C star. A star always pulls the asterisk F first, so it must finish the cheap path before it ever commits to an expensive one. Because the heuristic is too optimistic to ever inflate a good path above a bad goal. The good path always gets explored first. That's the whole proof in one breath. Trace it. From S, 2 options, through a costs 1 with heuristic 3, and F of 4, through B costs 2 with heuristic 1, and F of 3. S star expands the smaller F first, B. From B, reaching the goal G costs 3 more, total 5, F of 5. Now A's F is 4, still smaller, so expand A, but its route to G would cost 6, worse than 5, so we keep the cheaper one. Finally expand G. The expansion order is S, B, A, G, and the optimal path is S to B 2G, cost 5. Always order the frontier by F, lowest first. A second trace on a graph where the cheap path is the longer looking one. The edges, S to A costs 2 with heuristic 2, S to B costs 3 with heuristic 4, A to C costs 2 with heuristic 1, B to G costs 5, C to G costs 1. Predict the order before I move. From S, we see A with F equals 2 plus 2, 4, and B with F equals 3 plus 4, 7. Expand the smaller, A. From A node C has G of 4 and heuristic 1, F of 5. The frontier now holds C at 5 and B at 7. So expand C. From C, the goal G has G of 5 and F of 5. Expand it, done. The order is SA. CG. The path is S2A, 2C, 2G with cost 5. And look, B, sitting at F of 7, was VUC never expanded at all star. S star quietly skipped the whole expensive branch. Write G, H, and F in a little table, and these never go wrong. Your turn first, pause and run S star on this new graph before I do. The edges. S2P costs 2, S2Q costs 1, then P2T costs 5, Q2R costs 1, and our 2T costs 2. The heuristics, goal T at 0. S is 3, P is 4, Q is 2, R is 1. We start by expanding S with f equals 0 plus 3, 3. From S, we generate two nodes, P with G of 2 and heuristic 4, and F of 6, and Q with G of 1 and heuristic 2, and F of 3. The frontier holds P at 6 and Q at 3, so we take the smaller, expand Q. From Q, we reach R with G of 2, heuristic 1, F of 3. Now the frontier is R at 3 and P. Still waiting, at 6, expand R. From R the goal T has G of 4, heuristic 0, F of 4, it's below PS6, so we expand T and we're done. The expansion order is S, Q, R, T. The optimal path is S to Q to R 2T at total cost 4. And notice P, marooned at an F of 6, was never expanded once. The expensive first step priced itself right out of the search. Watch Greedy walk straight into the trap with numbers. Edges. S to A costs 1, A's heuristic 0, S to B costs 1, B's heuristic 1, then A to G costs a brutal 10, while B to G costs just 1. Greedy looks only at the heuristic. A's 0 beats B's 1, so it commits to A, then is forced down the 10 cost edge, total 11. S star looks at F equals G plus H. A's F is 1 plus 0, 1. B's F is 1 plus 1, 2. So S star tries a first, discovers the goal through a costs 11, but keeps B on the frontier at F of 2, expands it, and finds the goal through B for a total of asterisk 2 star. Greedy paid 11, S star paid 2. The heuristic alone is seductive and wrong. You must add the cost so far. The trap is reaching for the wrong sum. Use only the heuristic, and you're greedy. You'll chase a goal that looks close but lies down an expensive road. Use only the costs of R, and you waste time exploring uniformly. The exam answer is almost always the full F equals G plus H, and the optimality holds only when the heuristic is admissible. Write down G, H, and F for every node. That discipline is what earns the marks. Now games, where an opponent fights back. Minimax models two players with opposite goals. You are Max, trying to maximize the score. Your opponent is Min, trying to minimize it. You build the game tree of possible moves and assume perfect play. At max levels, you take the highest value, at min levels, the lowest, propagating those choices back up from the leaves. The value at the root is the best you can guarantee against a perfect opponent. Solve a small one. The root is max, with 2 min children. The left min sees leaves 3 and 5, and minimizing, picks 3. The right min sees 2 and 9 and picks 2. Now max, at the root, chooses the larger of 3 and 2, 3. So the game's value is 3, achieved by going left. Evaluate bottom up. Minimize at min nodes. Maximize at max nodes. Mechanical ones you see it. Minimax explores the whole tree, which explodes fast, so we prune. Alpha-beta pruning skips branches that can't possibly change the result. In our tree, once the left side guarantees max a 3, we examine the right min node and immediately see a 2. Since min will only go lower than 2, this branch can never beat the 3 we already have. So we stop, never even looking at the 9. Same answer, far less work. The more it prunes, the deeper you can search. Now a deeper one, 3 levels, 8 leaves, to drill the rhythm. The bottom internal layer is max. The first pair, 3 and 5, maximizes to 5. 6 and 9 give 9. 1 and 2 give 2. 0 and 7 give 7. So that layer reads 5. 9, 2, 7. The layer above is min. The left min takes the smaller of 5 and 9, 5. The right min takes the smaller of 2 and 7, 2. Finally, the root is max, choosing the larger of 5 and 2, 5. The game's value is 5. The trick is just to label each layer max or min before you start, then alternate without thinking. Let's prune the exact tree we just solved by hand. So you see what alpha beta skips. Go left to right. The left means first max child reads 3 then 5, value 5. That caps the left min at 5. A beta of 5. Its second max child opens with a 6. But 6 already meets that cap of 5, and a max node only climbs higher, so it can't lower the min below 5. We prune its other leaf, the 9. The left min settles at 5, lifting max's floor, alpha, to 5. Now the right min. Its first max child gives 2, which is below the floor of 5. So the right min is already 2 or less and can't beat 5. We prune its entire second child, leave 0 and 7 untouched. Root maximizes 5 against 2 5, exactly as before. We examined just 5 of the 8 leaves. 9, 0, and 7 never mattered. Let's name exactly which leaves get pruned, scanning left to right. The first min node, B, reads 3, 12, 8, minimizing to 3. That sets max a floor. Alpha equals 3. Move to the second min node, C. Its first leaf is 2. C is a minimizer, so C's value will be 2 or lower, already at or below our floor of 3. So C can never improve max's outcome. We prune the rest of C. Its leaves 4 and 6 are never examined. On to D. Its first leaf is 14, which doesn't trigger a cutoff, so we read 5, then 2, and D minimizes to 2. The root maximizes over 3, 2, 2, still 3. Final answer 3, and the only leaves we skipped were C's 4 and 6. Pruning never changes the value. It only skips the provably irrelevant. One more pruning problem. Fresh tree. Try predicting the cut before I trace it. Root is max, over 3 min nodes. Read left to right. The first min sees 8, 7, 3, and minimizes to 3. That sets max a floor, alpha of 3. The second min reads 5, then 6, then 9. Minimizing, it locks onto 5. And since 5 beats the old floor, alpha rises to 5. Now the third min, its first leaf is a 4. A min node only goes lower, so this node is already 4 or less, and 4 is below our floor of 5, so it can never improve max's result. We prune the rest of it. The leaves 1 and 2 go untouched. The root maximizes over 3, 5, and 4. Value 5. We examined 7 of the 9 leaves. The third nodes, 1 and 2 never mattered. Same trick every time. A min child whose running value has already fallen to or below max's. Alpha gets the axe. One insight they like to test. With perfect move ordering, alpha beta examines only about the square root of the leaves. Minimax would effectively letting you search twice as deep in the same time. The catch: it depends on order. Examine strong moves first and you prune aggressively. Examine them last and you prune almost nothing. The answer is identical to minimax. Pruning only removes the provably irrelevant. Switch to logic, reasoning with true and false. Propositional logic builds statements from atoms like P and Q using connectives. Not, and, or, implies, if and on leaf. A truth table lays out every combination. The one everyone trips on is implication. P implies question, it's false in exactly one case, when P is true but Q is false. A false premise implies anything. Burn that single row into memory. Half the logic questions hinge on it. 3 words to keep straight. A formula is valid. A tautology, if it's true in every row of the truth table. Satisfiable if it's true in at least one. And unsatisfiable if it's never true. And the engine of deduction is modus ponens. If you know P, and you know P implies Q, you may conclude Q. Chain those inferences and you can prove things mechanically, which is exactly what an automated reasoner does. Build a table and classify a real formula. If P implies Q and Q implies R, then P implies R. The chain rule of implication. 3 atoms, so 8 rows. The only way the whole thing could be false is if the 2 premises hold, but the conclusion fails. P implies Q true, Q implies R true, yet P true and R false. But if P is true and P implies Q, then Q is true, and Q true with Q implies our forces are true. So R can't be false. That contradiction can't happen in any row. So every row comes out true. The formula is valid, a tautology, and since it's true everywhere, it's automatically satisfiable too. Valid is the strong claim. Satisfiable just needs one true row. Two valid moves and one classic fake. Modus ponens. Given P and P implies Q. Conclude Q. Walk the arrow forwards. Modus tollens. Given P implies Q, and that Q is asterisk false S2. Conclude P is false too. Because if P were true, Q would have to be true, and it isn't. Both are airtight. The trap is affirming the consequent. Knowing Q is true and P implies Q does but not let you conclude. P rain implies wet ground, but wet ground could come from a sprinkler. The arrow runs one way. Only modus ponens forwards and modus tollens backwards are valid. Classify this formula yourself before the verdict. P or Q implies P and Q. Two atoms, so four rows. When both are true, the left side is true and the right side is true. So the implication is true. When P is true and Q false, the OR is true but the AND is false. True implies false. So the whole thing is false. By symmetry, P false and Q true gives false again. And when both are false, the OR is false. And a false premise makes the implication vacuously true. So the column reads true, false, false, true. Now read off the verdict. It's true in at least one row. So the formula is satisfiable. But it's false in some rows. So it is not valid, not a tautology. It's a contingency. And because it does have true rows, it certainly isn't unsatisfiable. Remember the ladder. Valid is the strong claim. True in every row. Satisfiable only needs one. And this formula clears the low bar, but not the high one. Propositional logic can't say all humans are mortal without listing every human, so first-order logic adds quantifiers and predicates. For all x and there exists an x, apply to predicates that take arguments, like human of x or loves x, y. Now all humans are mortal is one clean statement. For all x, if x is human, then x is mortal. The subtlety gate probes is the interplay of quantifiers. Everyone loves someone is very different from someone is loved by everyone. Order matters. Translate carefully and watch the quantifier order flip the meaning. Every student passed some exam becomes, for all x, if x is a student, then there exists a y. That is an exam. And x passed y. The for all sits outside. The there exists inside. So each student may pass a bag different exam. Now some exam was passed by every student. There exists a y, an exam, such that for all x, if x is a student, then x passed y. The there exists is now outside, naming fit one fit exam that everybody passed. Same words, swapped quantifiers, completely different claims. When a sentence mixes every and some, the one written first binds first. Get that nesting order right, and the marks are yours. For uncertainty, we return to Bayes. Now as a network. A Bayesian network is a directed graph where nodes are random variables and arrows mean direct influence. Rain points to wet grass. Each node carries a small table of its probability given its parents. The graph's real gift is encoding conditional independence. A variable, given its parents, is independent of its non-descendants. That structure turns an impossibly large joint distribution into a few small tables. That's the payoff. The full joint probability factorizes into a product of each node given its parents. Instead of one gigantic table, you multiply small ones. Take a simple network. A cause is B. A is true with probability 0.3. B given A is 0.9. B given not A is 0.2. Those three numbers fully specify the joint distribution of A and B. The graph's shape is doing the heavy lifting. Compute with it. The probability that A and B are both true is P of A times P of B, given A 0.3 times 0.9, which is 0.27. And the overall probability of B uses the law of total probability. Splitting on A 0.3 times 0.9 plus 0.7 times 0.2, 0.27 plus 0.14 equals 0.41. The very same total probability move from the start of this course. Now reading of a network. Here's the structural idea the graph buys you, called D-separation. In a chain, A influences B influences C. Information flows from A all the way to C. So A and C are as stock not pendant on their own, but the instant you preserve which P, the middle of the chain, you block the path. Knowing the cause right before C, the earlier cause tells you nothing extra. We say C is conditionally independent of a given B. Reading independence straight off the picture, which observations block, which paths, is what makes these networks tractable. And it's a favorite gate question. Put numbers on that chain. A is true with probability 1/2. B given A is 0.8, given not A 0.4. C given B is 0.9, given not B 0.3. First, a full joint. The chance A, B, and C are all true factorizes into P of A, times P of B given A, times P of C given B, 1/2 times 0.8 times 0.9, which is 0.36. Next, the marginal probability that B is true, summing over A by total probability. 1/2 times 0.8 plus 1/2 times 0.4, 0.4 plus 0.2 equals 0.6. Each piece is a tiny table. The product rebuilds the whole. Now the question gate actually asks, reasoning backwards from effect to cause, we observe that B is true. How likely is A its parent? That's Bayes' theorem on the network. P of a given B equals P of B given A times the prior P of A over the total P of B. The pieces are all in our tables, 0.8 times 0.5 on top, which is 0.4, and the total P of B we already computed, 0.6 on the bottom. 0.4 over 0.6 is 2/3, about 0.67. We started the prior at 1/2. Observing B raised our belief in a 2/3. Same flip as the rare disease test from part 1. Only now, the prior, likelihood, and evidence are all read straight off the graph. A different shape of network now. Two arrows meeting at one node, which the exam loves. Rain and a sprinkler each, on their own, point to wet grass. Rain is true with probability 0.2. The sprinkler, independently, 0.5. And wet given its two parents, 0.9. When both are on, 0.8 for rain alone, 0.7 for sprinkler alone, and 0.1 when neither. A little dew. First, a full joint. Pause and try it. The chance rain, sprinkler, and wet are all true factorizes into P of rain, times P of sprinkler, times P of wet given both. 0.2 times 0.5 times 0.9, which is 0.09. Now the marginal, the overall chance the grass is wet, by total probability across all four parent combinations, both on. 0.2 times 0.5 times 0.9, 0.09. Rain only, 0.2 times 0.5 times 0.8, 0.08. Sprinkler only, 0.8 times 0.5 times 0.7, 0.08. Neither, 0.8 times 0.5 times 0.1, 0.04. Add the 4. 0.09 plus 0.08 plus 0.2 equals 0.04, 0.49. With two parents you sum over 4 cases, not 2. Miss a row and the marginal is wrong. Asking a question of the network. What's the chance of the cause given the symptom is inference. Exact inference does it precisely by variable elimination. Take the variables you don't care about and sum them out. One at a time, reusing the partial results so you don't redo work. It gives the exact answer. And on small networks, it's quick. The problem is that on large, tangled networks, the cost can blow up, which forces a compromise. Run variable elimination end to end for the chance C is true. C only depends on A through B. So first we sum out A, which we already did. B is true with probability 0.6, false with 0.4. That single factor now summarizes everything A contributed. A is gone. Step 2, sum out B. C true is its chance given B true times 0.6 plus its chance given B false times 0.4. 0.9 times 0.6 plus 0.3 times 0.4. That's 0.54 plus 0.12, which is 0.66. Eliminate one variable. Reuse the result. Eliminate the next. That ordering is the entire algorithm. And it's why we never expand the full joint. When exact inference is too expensive, we approximate by sampling. Generate thousands of random scenarios consistent with the network's probabilities. Then simply count. What fraction of them have the property you're asking about? That fraction estimates the true probability. And the more samples you draw, the closer it gets, by the central limit theorem from the very first part. Trade exactness for speed, and let the law of large numbers carry you home. Artificial intelligence, locked. Problem solving is search. Breadth first is optimal only at unit cost. Uniform cost handles non-negative weights, and S star, with F equals G plus H, and an admissible heuristic, finds the optimal path. Games are minimax, made efficient by alpha-beta pruning that removes only the provably irrelevant. Logic deduces truths. Remember, implication is false in just one case, and modus ponens runs the arrow forwards. And Bayesian networks factorize uncertainty into small tables you can infer over, exactly by variable elimination or approximately by sampling. One subject left on the map, and it's the most efficient marks in the entire paper. 15 marks of general aptitude that too many people leave on the table. Let's not be them. 15 marks. The same general aptitude section sits in every single GATE paper, data science or not, and it is the highest return on the least preparation in the whole exam. Yet people pour months into machine learning and walk in cold on aptitude, leaking 5 or 6 easy marks. In a competition decided by fractions, that's a rank you just gave away. Let's secure all 15. General aptitude splits into verbal and numerical. Verbal ability tests grammar, vocabulary, and sentence sense. Fill in the blank, pick the correctly formed sentence, choose the right word. The trick isn't a bigger vocabulary overnight, it's elimination. Cross out options with a grammatical error or the wrong tone, and usually one survivor remains. Read the whole sentence, feel what fits, and eliminate ruthlessly. Reading comprehension gives you a passage and asks what it really says. The discipline? Answer only from the text, never from your own knowledge. Watch the qualifier words. All versus some, may versus must. Because the wrong options usually overstate what the passage actually claims, and distinguish what's directly stated from what's genuinely implied. The text is the only evidence that counts. Critical reasoning asks you to find the hidden assumption, the unstated belief an argument secretly leans on. Take this. A new bypass road will cut city traffic, so downtown air pollution will fall. Predict the missing link. The argument quietly assumes drivers will actually switch to the bypass. Here's the test that never fails. Negate each option and see if the argument collapses. If fucks nobody futty switches, traffic doesn't fall, and the conclusion dies. That's the assumption. The one whose opposite breaks the argument is always the answer. The quantitative half is school maths under time pressure. Percentages, ratios, averages, speed and distance, mixtures, a little probability. Nothing here is conceptually hard. The challenge is doing it quickly and not falling for the built-in traps. And there's almost always a built-in trap, because the obvious answer is usually the wrong one. Let me show you the most famous one. A price goes up 20%, then down 20%. What's the net change? Predict it? The tempting answer is 0. Up 20, down 20, surely it cancels. It does not. The fall is 20% of a J bigger book a number than the rise was. Multiply it out. 1.2 times 0.8 is 0.96. A 4% par tick decrease star. Percentages don't add. They multiply. That single insight rescues a whole family of GA questions. Now the same multiplying idea, dressed as profit and loss. A shopkeeper marks an item 40% above cost, then advertises a 25% discount. Profit or loss? Predict the sign? Marking up gives 1.4 times the cost. The discount keeps 75% of it's that good. So multiply 1.4 times 0.75. That's 1.05. He still makes a 5% profit. A big discount on a bigger marked price. The chain of multipliers tells you exactly where you land. A mixtures problem, and the trick is to follow the part that doesn't change. 40 liters of a solution is 90% milk. How much water must you add to dilute it to 60% milk? Predict. The water you pour in has no milk, so the chalk amount HEQ milk never moves. 90% of 40 is 36 liters, fixed. After adding, that same 36 liters must be 60% of the new total. So the new total is 36 over 0.6, which is 60 liters. You started with 40, so you add 20 liters of water. Anchor to the unchanging quantity, and dilution problems melt. Here is the speed trap gate plants every year. You drive to a town at 40 kilometers an hour and return along the same road at 60. What's your average speed for the whole trip? Predict it. Almost everyone says 50, the average of 40 and 60. Wrong. You spend jug more time at the slower speed, so it pulls the average down. For equal distances, the right tool is the harmonic mean. 2 times 40 times 60 over 40 plus 60. That's 4,800 over 148 kilometers an hour, not 50. Equal distances, harmonic mean, never the plain average. A classic. A train 240 meters long crosses a platform 360 meters long, traveling at 60 kilometers an hour. How long does it take? Predict the distance first. To fartes fully astes clear the platform, the train must cover its own length plus the platform. 240 plus 360, 600 meters. Now convert the speed. 60 kilometers an hour is 60,000 meters over 3,600 seconds, about 16.67 meters a second. 600 divided by that is 36 seconds. The whole game is remembering to add both lengths. Work rate problems. Worker A finishes a job alone in 12 days. Worker B in 18. Together, how long? Predict. The trap is to average the days. Instead, add their wish rate star. A does 1/12th of the job a day, B 1/18th. Over a common denominator of 36. That's 3/36 plus 2/36, 5/36 of the job every day. Flip it to get the time. 36 over 5, 7.2 days. Add the rates, then invert. Days never add. Work per day does. Accounting and probability quickie. First, how many ways to arrange the letters of the word level? 5 letters. But the L repeats and the E repeats. So it's 5 factorial, 120, divided by 2 factorial for the LS and 2 factorial for the ES. That's 120 over 430 arrangements. Second, roll 2 dice. Chance the sum is 7. Out of 36 equally likely pairs, 6 gives 7, 1 over 6. Divide out the repeats, count the favorable cases. That's most of GA probability. Data interpretation hands you a chart or table and asks you to read and compute. Percentage changes, ratios, which category leads, what the average is. The skill is calm extraction. Find the exact two numbers the question needs, ignore the rest of the busy chart, and compute. Most mistakes here aren't maths errors. They're reading the wrong cell. Slow down for 1 second to locate the right numbers. Then move fast. Quick one. Sales were 40 in the first quarter, 60 in the second. What's the percentage increase? Always over the ASIC original S. The rise of 20 divided by the starting 40 is 50%. The classic error is dividing by 60, the new value, and getting 33. Percentage change is always measured against where you started, anchored to the original number. Every time. A fuller read. Two computations of one chart. Product A sells 120 in January, 150 in February. Product B sells 80, then 120. First, the ratio of total January sales to total February sales. January is 120 plus 80, 200. February is 150 plus 120, 270. 200 to 270 reduces to 20 to 27. Second, which product grew faster in percentage? A rose 30 on a base of 120, 25%. B rose 40 on a base of 80, 50%. B grew twice as fast, even though A sold more. Percentage growth depends on the base, not the size. Analytical and logical reasoning covers sequences, puzzles, seating arrangements, and syllogisms. Take the series 2, 6, 12, 20, 30. Look at the gaps. 4, 6, 8, 10. Rising by 2 each time. The next gap is 12, so the answer is 42. Find the pattern in the asterisk differences, asterisk when the numbers themselves don't obviously progress. Most series questions crack the moment you look one level down. And a syllogism, where intuition betrays you. All cats are mammals? Some mammals are pets. Therefore, some cats are pets. It feels right, but it's invalid. Draw the circles. The pet mammals might be exactly the asterisk non-cats mammals, dogs and rabbits, with no cat among them. Nothing forces an overlap. In logic, some A are B never lets you conclude a specific A is B. Test these with a quick Venn diagram and trust the diagram over your gut. One more series, because the technique is worth drilling. 3, 6, 11, 18, 27. Then what? The numbers jump unevenly, so drop a level and read the gaps. 3, 5, 7, 9. The odd numbers in order. The next gap must be 11. So the answer is 27 plus 11, 38. Same habit every time. When a sequence looks irregular, the differences are usually telling a clean, simple story. Blood relations puzzles look tangled until you draw them. A is B's sister. C is B's mother. D is C's father. How is A related to D? Predict it. Sketch a quick tree. A is B's sister. So A is also a child of C, the mother. D is C's father, one generation above C. So D is 2 generations above A, which makes her the granddaughter of D. Never solve these in your head. Draw 3 boxes for 3 generations, and the answer reads straight off the page. Seating arrangements are pure bookkeeping. Let the clues place people one at a time. 5 chairs in a row. R sits at the left end. S sits next, then P, with Q immediately 2Ps right and T on the far right. Slot them in R, S, P, Q, T. The question asks, who's in the middle chair? The third seat, and that's P. The discipline is to draw the empty seats first and pin each person only when a clue forces it. Don't guess ahead of the clues. Spatial aptitude tests your mind's eye. Folding a flat net into a cube, rotating a shape, spotting the odd one out, telling a rotation from its mirror image. There's no formula, it's practice. The one habit that helps. Fix a single reference feature, one face, one corner, and track only that through the transformation, instead of trying to hold the whole shape at once. Anchor, then rotate. Now the strategy that actually wins marks. Do general aptitude first, while you're fresh and the clock isn't yet scaring you. About 20-25 minutes to lock in those 15 marks. They're quicker per mark than anything in the core paper. Secure the easy 15, build momentum and confidence. And Tessic then, turn to the 85, where the real fight is. Never save aptitude for the panicked final minutes. General aptitude, locked, and with it, the entire map is lit. Eliminate your way through verbal and find the assumption by negating it. Remember, percentages multiply, never add, and always measure change against the original. For equal distances, average speed is the harmonic mean, not the plain average. Hunt patterns in the differences and draw the picture. A Venn for logic, a family tree for relations, a row of seats for arrangements. On exam day, claim these 15 marks first. Easy marks are still marks, and ranks turn on them. You've now seen every subject gate data science can ask. The map is complete. All that remains is to turn knowledge into a score, strategy, timing, and a rapid-fire round of real exam questions. The exam lab to finish. You've learned the whole syllabus, but the exam doesn't reward knowing. It rewards chatty scoringus in 3 hours under pressure with traps laid for you. Two people with identical knowledge can walk out with very different ranks purely because one managed the clock, the guesses, and the panic, and the other didn't. So this final part is pure strategy and practice. How the marks really break down, how to spend your time, exactly when a guess pays off, and a rapid round of real exam-style questions where you predict before I solve. This is the part that turns everything you've understood into an actual number on a results page. Let's convert knowledge into rank. First, know the battlefield. 65 questions, 100 marks. Roughly 30 of them are 1-mark questions and the other 35 are 2-mark questions. 30 plus 35 is 65 and 31s plus 35 twos is exactly 100 marks. The 2 markers, being worth double and usually multi-step, are where the paper is genuinely won or lost. General aptitude is 10 of those questions for 15 marks, 5 ones and 5 twos. The other 85 marks are your core data science and AI. Spend your energy in proportion to the marks, not your comfort. 3 hours is 180 minutes. For 65 questions, divide, and that's under 3 minutes each on average, about 2 minutes 45 seconds. But never spend it evenly. Make 2 passes. First pass, sweep the whole paper, answering everything you can do in under a minute or two, and flag anything slow. There's a mark for review button. Use it. Second pass, return to the flagged hard ones with whatever time remains. This way, a single brutal question never robs you of 10 easy marks sitting later in the paper. Let me put real numbers on that budget. Reserve 15 minutes at the very end for review and for the questions you flagged. 180 minus 15 leaves 165 minutes of actual solving. Give general aptitude about 20 minutes for its 10 questions. That's 2 minutes each, and GA is fast marks. 165 minus 20 leaves 145 minutes for the 55 core questions, which is roughly 2 minutes 36 seconds apiece. Now you're not guessing where the time goes. You've already spent it on paper before the clock starts. And the guessing rule, which we proved back in orientation. Numerical and multiple select questions carry no negative marking, so never, ever leave one blank. A guess can only help. On ordinary multiple choice, a blind guess among 4 is exactly break-even. But the moment you eliminate even one option, the odds tip in your favor and you should guess. Rule of thumb, attempt every NAT and MSQ, and guess on MCQs only once you've ruled something out. Let's actually do the expected value arithmetic, because it's worth seeing once. Take a 1-mark multiple choice with 4 options. A wrong answer costs 1/3. Guess blindly. You're right 1 time in 4 for +1 and wrong 3 times in 4 for -1/3. A quarter minus 3 times 1/3, which is a quarter, 0. Dead break even, exactly as promised. Now eliminate just one option, leaving 3. Right 1 time in 3 for +1. Wrong 2 times in 3 for -1/3. A third minus 2/9 is 1/9, about plus 0.11, positive. One crossed out option literally turns a coin flip into a paying bet. The same logic scales to a 2-mark question, where the penalty is 2/3. Blind. A quarter times plus 2 is a half. 3/4 times minus 2/3 is a half the other way. 0 again. Notice the break-even point never moves. That's by design. But eliminate one option, and the upside doubles with the stakes. A third times plus 2 is 2/3. Minus 2/3 times 2/9 leaves 2/9, about plus 0.22. So the rule isn't superstition. It's expected value. Cross one out, then guess. Now the rapid round, quick questions from across the whole map at exam speed. Treat each as the real thing. When I pose it, pause the video and predict. Asterisk then is to watch me solve. This is the retrieval practice that actually moves marks. A dozen problems. Every subject, fresh from the question bank. Pencils up. Go. Probability. First, roll 2 fair dice. What's the chance of at least 1 6? Predict it. The phrase at least 1 is your cue to flip to the complement. The chance a single die avoids 6 is 5/6. So both avoid it with probability 5/6 squared, 25 over 36. Subtract from 1, 11 over 36, about 31%. When at least 1 appears, compute none and take 1 minus it, far faster than adding cases. A subtler one, and a famous trap. A family has 2 children, and you're told at least 1 is a boy. What's the chance both are boys? Predict. Most people say 1/2, reasoning that the other child is equally likely a boy or a girl, and most people are wrong. The catch is that you weren't told which child is the boy, so you must list the equally likely families. Boy, girl, girl. At least one boy rules out only girl, leaving 3 equally likely cases. Both boys is just one of those 3, so the answer is 1/3, not a half. Conditioning shrinks the sample space, and you must shrink the denominator right along with it. Linear algebra. Find the determinant of this 3x3 matrix. But look at its shape first. Everything below the diagonal is 0. It's upper triangular. Predict. For any triangular matrix, the determinant is simply the product of the diagonal entries. The numbers above the diagonal don't matter at all. 2 times 3 times 4 is 24. Spot the triangle and you skip every bit of expansion. Instant mark. Another, purely conceptual, no numbers to grind. A 3x3 matrix has 2 identical rows. What's its determinant? Is it invertible? And is 0 one of its eigenvalues? Predict all 3. Identical rows mean the rows are linearly dependent, so the determinant is 0. A 0 determinant means the matrix is singular, not invertible, and a 0 determinant means 0 is an eigenvalue, because the determinant is the product of the eigenvalues. 3 facts. 1 observation. Dependent rows collapse the whole matrix. Calculus. Find the minimum value of f of x equals x squared minus 4x plus 7. Predict. It's an upward parabola, so its one turning point is the minimum. Differentiate. 2x minus 4, set to 0, gives x equals 2. Plug back in, 4 minus 8 plus 7 is 3. The minimum value is 3, reached at x equals 2. Derivative to 0 locates a substituting back, gives phi never stop at the x value. A classic optimization. Among all rectangles with perimeter 20, which has the largest area. Predict. Perimeter 20 means x plus y is 10. So y is 10 minus x, and the area is x times 10 minus x. Differentiate. 10 minus 2x, set to 0, x equals 5, which makes y5 2, a square. Its area is 5 times 5, 25. The maximum area rectangle for a fixed perimeter is always the square. Here, that's 25 square units. Algorithms, complexity. A loop where the outer counter I runs to n, and for each I, the inner loop runs I times. How many operations total? Predict the big O. The inner work is 1, then 2, then 3, up to n. That sum is n times n plus 1 over 2. The leading term is n squared over 2, and big O drops the constant, so it's order n squared. A triangular nested loop is quadratic, even though the inner loop isn't always full. One recurrence, and watch it isn't the merge sort one. T of n equals to T of n over 2, plus a constant 1, predict. To subproblems of half the size, but only constant work to combine them. The splitting creates n leaves, and with just constant work per level, the leaves dominate. So this collapses to order n, linear. Compare it to merge sorts plus n, which gave n log n. The combined cost is what decides it. Constant gives linear. Linear gives n log n. Databases attribute closure. A relation with columns A, B, C, D, E, and 3 dependencies. A to B together gives C. C gives D. D gives E. Is A to B a candidate key? Predict. Start the closure with A and B themselves. A to B pulls in C, then C pulls in D, then D pulls in E. So A to B determines every column, making it a super key. And since neither A nor B alone could start that chain, it's minimal. A genuine candidate key. Chase the closure. If it swallows all attributes, you've found a key. Machine learning. Decision tree purity. A node holds 8 positives and 8 negatives. What's its Gini impurity? Predict. Gini measures how mixed a node is, the chance you'd label a random item wrong if you guessed by the node's class proportions. Each class is half the node, so the proportions are 0.5 and 0.5. Gini is 1 minus the sum of squared proportions. 1 minus a quarter plus a quarter, which is 1 minus a half, 0.5. That's the worst possible value for two classes. A 50-50 node is maximally impure, and a good split should drive those child nodes towards 0, pure node, Gini 0. Perfectly even split, Gini 1/2. And the tree greedily picks whichever split drops it the most. Another from machine learning, the distance behind k-nearest neighbors. How far is the point 3? 4 from the origin? Predict. It's the straight line Euclidean distance. Square root of 3 squared plus 4 squared, square root of 9 plus 16, square root of 25, 5. The familiar 3-4-5 triangle. And here's the exam hook. Because KNN measures exactly this. A feature on a huge scale would dominate the distance, which is why you always standardize your features before running it. Artificial intelligence. Heuristics for S-star. A heuristic guesses the remaining cost to the goal as 4, but the true cheapest cost from there is only 3. Is the heuristic admissible? Predict. Admissible means it must never rush-estimate for the real cost. 4 is bigger than 3. So this heuristic overestimates. It is not admissible, and the consequence matters. With an inadmissible heuristic, S-star can be misled into returning a path that isn't actually the shortest. Underestimate or be exact. Never overshoot. And aptitude, to close the round, with its favorite trap. A car drives one way at 60 kilometers an hour and returns the same distance at 40. What's the average speed for the whole trip? Predict. The tempting answer is 50, the simple average, and it's wrong. Average speed is total distance over total time, and the car spends S-ping law at the slower speed, which drags the average down. The shortcut for equal distances is the harmonic mean, 2 times 60 times 40, over 60 plus 40, 4,800 over 148. Average speed is never the plain average of two speeds, weighted by time. 12 questions. Every subject on the syllabus. And did you notice how a few core moves kept coming back? The complement trick, shrinking a sample space, products of a diagonal, chasing a closure, the cost that dominates a recurrence. Gate doesn't test 1,000 facts. It tests a few deep ideas, dressed up 1,000 ways. Learn the idea, and every disguise falls off. Before you go, the trap wall. Every ambush gate sets gathered in one place. forgetting the base rate. So a rare disease and a positive test still mean you're probably fine. Confusing independent with mutually exclusive when they're nearly opposites. Reading correlation as causation. Assuming a real matrix has real eigenvalues, rotations don't. Skipping the endpoints when you optimize on a closed interval. Quoting Quicksort's average as its worst case, when its worst is n squared. Trusting accuracy on imbalanced data, where predicting the majority looks brilliant and tells you nothing. Forgetting to scale features for KNN. Using only the heuristic instead of G plus H in S star. Misjudging when an implication is false. Only true implies false fails. And adding percentages that should multiply. Every one of these has a wrong answer that fits feels right, which is exactly why it's on the paper. Name the trap before it's sprung, and it stops being a trap. A last word on the day itself. The paper will throw one or two monsters at you. Let them go, flag them, and move on. They are worth the exact same 2 marks as a question you can do in 30 seconds. So spending 10 minutes wrestling one is the most expensive mistake in the room. Your job is to harvest every mark you've earned the right to, not to win a duel with the hardest question. When the nerves spike, breathe once and fall back on the routine. 2 passes, flag and return, fill every box. The routine carries you when adrenaline won't. Stay calm. Trust the preparation you've just done. You know this material now, deeply, and you've earned the right to walk in certain of it. Let me make those 2 passes concrete with numbers. First pass, about 90 minutes. You sweep all 65 questions and clear the ones you know cold. Say 45 of them. Roughly 2 minutes each, and you flag the remaining 20 without agonizing. Second pass, about 55 minutes. You crack maybe 12 of those 20 with focused effort. That leaves 8 genuinely hard ones. And on those you never leave a blank. Fill every numerical and multiple select. And on the multiple choice, eliminate what you can and then guess. You walk out with 65 answers and 0 empty boxes. That's how a prepared mind converts to a score. Look how far you've come. Probability and statistics, linear algebra, calculus and optimization, programming and algorithms, databases, machine learning, artificial intelligence, and aptitude. 8 lands, 1 connected map. And you didn't memorize it. You understood it. Each idea hanging off the last. That is exactly how a top rank is built. Not from cramming, but from seeing how it all fits. That's the entire GATE data science and AI syllabus in one sitting. Come back to any chapter whenever you need it. That's what the timestamps are for. If this made the whole map finally click, subscribe, and the next intuitive video will find you. Now go and earn that rank. You've got this.